Hello there, and welcome to Physics with William, where we take familiar parts of the world, give them a little more attention than they usually receive, and see what the physics has been doing while the rest of us were busy making tea, looking for our keys, or wondering why one floorboard in the house has suddenly decided to become extremely talkative at night. Tonight we're going to explore something that reaches you almost every moment you're awake, and quite a few moments when you're asleep as well. Sound is so ordinary that it is easy to forget how strange it really is. A voice crosses a room and arrives at your ears. A door closes downstairs and somehow you know about it from the other end of the house. A bird calls from a tree you cannot see. A car passes outside. Rain touches the window. Pipes knock gently somewhere behind a wall. Every one of these events creates a disturbance, and somehow that disturbance makes a journey through matter until a tiny part of your inner ear responds to it. Most of the time, the journey happens so quickly that we barely think of it as a journey at all. We hear the sound and simply assume that the event and the hearing of it happened together, but they did not. Sound needed time to reach you, and that means sound has a speed. That immediately gives us a question which sounds simple until we begin pulling at it. Where does sound get its speed from? Why should a clap, a violin note, a dog barking, or the sudden dropping of a spoon travel through air at a particular rate? Why not twice as fast? Why not half as fast? Why does the answer change if the sound travels through water instead of air? Why can vibrations move through many solids even faster? And why does a change in temperature alter the speed at which sound crosses the atmosphere? These are not separate curiosities. They are all clues pointing toward the same idea. Sound does not come with one fixed speed that belongs to sound itself. Its speed is determined by the material carrying it. Air gives sound one speed. Water gives it another. Steel gives it another. Even the same air can give slightly different answers when its temperature changes. So when we ask how fast sound travels, we are really asking something about matter. We're asking how quickly one part of a material can respond when another part of that material is disturbed. Before we follow that disturbance in detail, have a listen to whatever is around you right now. Where are you listening from tonight, and what is the most distant sound you can notice from where you are? Maybe you can hear traffic several streets away. Perhaps there is wind outside, someone walking in another room, a television through a wall, or a clock whose ticking seems perfectly reasonable during the day and somehow becomes a personal insult after midnight. If the room is very quiet, you may notice your own breathing, or the small sounds made by the building around you. Whatever you hear, the sound has crossed some amount of space to reach you. It may have travelled through air, through walls, through floors, or through several materials along the way. Even before we understand the physics, your ears are already performing a continuous demonstration of it. If you enjoy these gentle journeys through science, and find them useful for winding down while learning something along the way, you can leave a like and subscribe to Physics with William. It helps this quiet corner reach other curious listeners as well. For now, get comfortable, let the room make whatever little noises it wants to make, and we can begin with one of the easiest ways to notice that sound really does take time to travel. Your thunderstorm provides the demonstration for free. Lightning flashes somewhere in the distance and you see it almost at once. Then there is a pause. A second passes, perhaps several, and only afterward does the thunder arrive. The lightning and the thunder were produced by the same general event, yet your eyes and ears report them at different times. The reason is not that thunder waits politely before beginning. The sound starts immediately, but it moves much more slowly than the light. The greater the distance between you and the lightning, the longer the sound has to travel and the larger the delay becomes. A similar thing happens if you watch somebody from far across a field strike two objects together. At close range, the movement and the sound appear perfectly synchronized. Move far enough away, and you can see the impact before you hear it. Nothing about the sound source has changed. The delay has simply become large enough for human senses to notice. Sound was always taking time. Distance has merely exposed the fact. In ordinary air near comfortable room temperature, Sound travels at roughly 343 meters each second. That is fast compared with almost anything we experience directly in daily life. A sound could cross a large room before you had the slightest chance of noticing the delay. Yet on the scale of landscapes, storms, aircraft, and large explosions, that speed becomes very noticeable. It is also surprisingly modest compared with many other things in physics, especially light. This is why the flash of lightning seems immediate while the thunder wanders in later. Sound is quick enough for conversation, but not quick enough to hide its travel time across long distances. The interesting part, though, is that the number itself is not the explanation. Saying that sound moves at a certain speed is like saying that a car is travelling at 50 miles an hour. We still have not explained why. What physical process allows the disturbance to move and what sets the pace? A natural first guess might be that sound is some kind of substance moving through the air. Perhaps when someone speaks, something leaves their mouth, travels across the room and enters your ears. There is a tiny piece of truth in the image because energy certainly moves from the speaker toward the listener, but the air itself does not make that journey in the way a thrown ball would. If it did, every conversation would involve a steady stream of air rushing from one person to another. Loud concerts would be extremely windy places. Instead, the individual molecules of air mostly remain in the general region where they started. They move around constantly, of course, because gas molecules are always in rapid microscopic motion. But the sound does not require a particular molecule to travel all the way from the source to your ear. What travels is disturbance. Imagine a loudspeaker playing a low note. The visible part of the speaker moves outward and then inward again. When it moves outward, it pushes against nearby air. The molecules in that region become slightly more crowded than they were a moment before. That crowded region pushes on the air beside it. Then the speaker moves inward, leaving a region where the molecules are slightly less crowded. The repeated motion creates a sequence of compressions and expansions that spreads away from the speaker. The air molecules move back and forth by very small amounts, while the pattern itself travels across the room. This distinction is one of the most useful ideas for understanding sound. The material moves locally. The disturbance travels much farther. There are many everyday comparisons that can help. Think of a long line of people standing close enough that each person can gently nudge the next. The first person leans forward and bumps the second shifts and bumps the third. Soon the disturbance has travelled along the entire line even though nobody has walked from one end to the other. Or picture a crowded stadium performing a wave. Each person only stands up and sits down. The spectators remain near their seats, yet the wave can move around the stadium. Sound is not exactly like either example, because gases involve huge numbers of particles moving and colliding in all directions, but the basic lesson survives. The speed of the travelling pattern is not the same thing as the speed of the individual pieces of the material. Once that is clear, the question of speed begins to change shape. Instead of asking how quickly sound itself decides to move, we can ask how quickly one part of the material can affect the next. Suppose a small region of air is compressed. The molecules there push outward. How quickly does the neighbouring region respond? How rapidly can that response be passed onward? The answer depends on the physical character of the material. Some materials resist compression strongly. Some are easier to squeeze. Some contain particles with greater inertia, meaning they are more resistant to having their motion changed. These properties work together to determine how rapidly a pressure disturbance can spread. Sound therefore borrows its speed from the medium carrying it. The word medium in this context is much less mysterious than it may sound. It simply means the material through which the sound travels. Air is a medium, water is a medium, wood, glass, rock, steel, and the tissues of your body can all carry sound in different ways. If you place your ear against a table and somebody gently taps the other end, the sound can become surprisingly distinct because the vibration is travelling through the solid material as well as through the surrounding air. Anyone who has lived in a building with enthusiastic neighbours will already have conducted several uncontrolled experiments in structural acoustics. A footstep above you may arrive through the ceiling. A drill several rooms away can seem strangely close because vibrations have entered the walls and floors. Sound does not care whether the route is convenient. If matter can transmit the disturbance, the sound can use it. Water gives another familiar example. Put your ears beneath the surface of a swimming pool and the soundscape changes immediately. Splashes, knocks, voices and mechanical noises take on a different quality. Some sounds may seem louder or harder to locate. The reason is partly that water transmits sound differently from air, and partly that your ears evolved mainly for listening to sounds that arrive through the atmosphere. The important point for us is that sound moves faster through water than it does through ordinary air. That sometimes surprises people, because gas molecules seem so free to move. Surely, you might think, if the particles can move easily, the sound should travel faster. But the speed of sound is not mainly about giving one particle enough room to race toward the next location. It is about how effectively a disturbance can be communicated through the material. In a liquid, particles are much more closely packed than they are in a gas, and the material generally resists compression more strongly. Disturb one region, and the neighbouring regions respond efficiently. Many solids carry the process further. Their particles are held in arrangements where a displacement can produce a strong restoring response. Push one part slightly away from its normal position, and the forces inside the material tend to pull or push it back. That response can pass along the structure rapidly. As a result, sound can move through many solids much faster than through air. A vibration travelling through steel, for example, can outrun the same disturbance moving through the atmosphere nearby. The particles in the steel are not sprinting from one end of the object to the other. The information that a disturbance has occurred is being handed through the material very efficiently. This leads to a useful way of thinking about the origin of sound speed. A material needs two broad qualities for sound to travel through it. It needs some ability to push back when disturbed, and it also has inertia. The pushback helps transmit the disturbance. The inertia resists changes in motion. If a material responds strongly to being compressed or stretched, neighbouring regions can influence each other quickly. If a great deal of mass has to be accelerated during that response, the process is harder to change rapidly. The actual speed emerges from the balance between those tendencies. We do not need an equation to understand the idea. Imagine trying to send a motion through two different systems. One snaps back rapidly whenever it is disturbed. The other responds sluggishly. The first can pass the disturbance onward more quickly. Now make the pieces of either system much harder to accelerate and the response becomes slower. Real materials are vastly more complicated, but the same general competition between stiffness and inertia sits underneath the speed of mechanical waves. Air has its own version of this balance. Compress a pocket of air and the pressure rises. The compressed gas pushes outward, trying to restore a more even distribution. That pressure response allows the disturbance to continue. At the same time, the gas has mass, so it cannot react infinitely quickly. Under a particular set of conditions, those properties combine to produce the familiar speed of sound in air. Change the conditions and the speed changes. This is why the number you may have learned for the speed of sound is not a universal constant of nature. It is a useful value for a particular kind of air at a particular temperature. Temperature matters especially strongly in gases. Warm the air and its molecules on average have more microscopic kinetic energy. Their motion becomes more energetic and pressure disturbances can be communicated differently through the gas. The result is that sound travels faster in warmer air than in colder air. The difference is not large enough to make a conversation sound delayed on a winter morning, but it is measurable and important in situations where precision matters. The atmosphere can also contain layers at different temperatures, and those layers can change the path that sound follows. This is one reason distant sounds sometimes seem unusually clear under certain weather conditions. A road or railway that is normally faint may suddenly appear to be much closer. The source has not moved. The atmosphere between you and the source has changed the way the sound travels. Something else becomes clear once we understand that sound needs a material response. If there is no material, ordinary sound has nothing to travel through. Imagine a ringing device sealed inside a transparent chamber. At first, the chamber contains air, so the vibration of the device disturbs that air and sound can reach the walls of the container. If more and more air is removed, fewer gas particles remain to carry the disturbance. The sound becomes weaker. With a sufficiently good vacuum, the device can continue vibrating while almost no sound crosses the empty region. The source is still doing its job. The missing piece is the medium. There is no continuous material available to pass the mechanical disturbance onward. This is why space, despite its dramatic reputation, is mostly silent in the ordinary acoustic sense. An explosion in empty space cannot send a booming sound through a vacuum toward a distant astronaut. Films quite sensibly ignore this because two spacecraft drifting past one another in complete silence would make for a rather different sort of action sequence. Real physics is less concerned with soundtrack design. Vibrations can certainly travel inside a spacecraft. They can move through its metal structure and through the air inside the cabin. Waves can also travel through gases and other matter found in space. But where there is a true vacuum, there is no ordinary sound transmission, because there is no chain of matter available to carry the disturbance. The dependence on a medium also tells us why asking for the speed of sound without saying anything else is slightly incomplete. It is rather like asking how quickly something can move without telling us what the thing is. Sound in air has one range of speeds, sound in water has another. Sound in rock, wood, glass or steel can be different again. Even within one material, temperature and other conditions can matter. There is no single cosmic speed assigned to every sound wave everywhere. Light behaves very differently in this respect. Sound is tied to matter in a much more direct way. Its speed emerges from the mechanical behaviour of the substance carrying it. You can notice consequences of this around your own body. When you speak, you hear yourself by more than one route. Some of the sound travels through the air from your mouth to your ears, but vibrations also move through the bones and tissues of your head. This changes the balance of frequencies reaching your inner ear. Then you hear a recording of your own voice and wonder who this unfamiliar person is and why everyone else has apparently been allowing them to speak on your behalf for years. Part of the difference comes from losing the vibration path through your own head. The recording mainly gives you the version of your voice that travelled through air, which is much closer to what other people normally hear. Musical instruments offer the same lesson in a more deliberate form. A guitar string vibrates, but the string alone does not move enough air to produce the full sound we associate with the instrument. Its vibration is transferred into the body of the guitar, which moves more air and helps radiate the sound outward. A piano sends vibrations from strings into a soundboard. A drum depends on the motion of a stretched surface and the air around it. Wind instruments create organized vibrations in columns of air. In each case, the audible result depends on disturbances passing through different materials. The speed at which those disturbances move is part of what allows the whole system to behave as it does. Even echoes quietly demonstrate the same physics. If you call toward a distant wall or cliff, the sound travels away from you, reaches the surface, reflects, and travels back. The delay tells you that the journey took time. If the speed of sound through the air changed, the echo would return at a different moment, even if the wall remained exactly where it was. This makes echoes useful for measuring distance, and the same general idea appears in sonar systems, where sound waves travel through water, reflect from objects, and return to a detector. To interpret the travel time properly, you need to know how quickly sound moves through the medium. The medium is not just scenery, it is part of the measurement. The speed of sound becomes even more dramatic when an object begins moving through a medium almost as quickly as the sound disturbances it produces. An aircraft pushes on the air around it, and those pressure changes normally spread ahead of the aircraft. As the aircraft moves faster, it begins catching up with its own disturbances. Eventually, the pressure waves can crowd together and form a shock. That is where sonic booms enter the story. The phrase sound barrier can make it seem as though there is an invisible wall waiting at one particular speed, but there is no wall. What matters is the relationship between the aircraft and the speed at which pressure information can move through the surrounding air, change the air conditions and that local speed changes as well. All of these examples point back to the same answer. Sound gets its speed from the medium, because sound is the motion of a disturbance through that medium. The source begins the event, but the material determines how rapidly the event can be passed onward. The air does not receive an instruction from the sound telling it how fast to move. The air responds according to its own physical properties. Water responds according to different properties. Solids respond according to theirs. Temperature changes those responses. Density matters, but not by itself. Stiffness matters, but not by itself. The speed comes from the way these properties work together. That is why the simple question of how fast sound travels opens a much larger door. To answer it properly, we have to stop thinking of sound as a thing flying through space and start thinking about what the material is doing moment by moment. When a speaker cone moves outward, what happens to the layer of air touching it? What happens to the next layer? How does a tiny compression become a travelling wave? How far do the individual molecules actually move? If the sound reaches your ear from the other side of the room, did any molecule near the speaker make that entire trip? And if not, what exactly did? Those questions bring us closer to the real machinery of sound. The answer is hidden in a rapid chain of local interactions, with each small region of matter responding to its neighbours and passing the disturbance onward. Once we follow that relay carefully, the speed of sound stops looking like an arbitrary number and starts looking like the natural consequence of how matter responds when it is pushed. The easiest way to misunderstand sound is to imagine that something leaves the source and travels all the way to the listener. It is such a natural picture that our language encourages it. We say that a sound travels across the room, reaches our ears, comes through the wall, or carries across a valley. All of that is useful language, but it can quietly suggest that sound behaves like a tiny invisible object, flying from one place to another. What actually happens is much more interesting. The sound moves across the room, but the air that carries it mostly does not. The molecules near the speaker remain near the speaker. The molecules near your ear remain near your ear. Between them is an enormous chain of interactions, each one passing a disturbance to its neighbour. Nothing needs to make the entire journey. The message travels because matter responds locally, one small region at a time. Imagine a loudspeaker sitting at one end of a quiet room. When the speaker is turned off, the air in front of it is already busy. Air may look still, but on the microscopic scale its molecules are moving rapidly in every direction, colliding with one another and bouncing from surfaces around the room. There is no neat arrangement and no little rows waiting patiently for the music to begin. The molecules form a restless gas moving constantly. Even in complete silence, the microscopic world is anything but quiet. What silence really means is that there is no organised pressure disturbance large enough for your ears to interpret as sound. Now the speaker cone moves forward. It pushes into the air immediately in front of it. The molecules there cannot simply vanish to make room, so they're crowded slightly closer together. This creates a region of higher pressure. The molecules in that crowded region are already moving and colliding, but now the balance has changed. They push more strongly on the air just beyond them. That neighbouring region becomes compressed as well. The first region does not need to travel across the room. It only needs to influence what is beside it. Then that region influences the next one, and the next one does the same. The compression begins moving outward even though the individual molecules only shift over relatively small distances. The speaker cone then moves backward. The air immediately in front of it becomes slightly less crowded. Instead of a compression, there is now a region of lower pressure. Surrounding air moves into that region, and this change also passes outward. If the speaker keeps moving back and forth, it creates a repeating pattern of slightly higher pressure followed by slightly lower pressure. The result is a travelling pressure wave. Your ear eventually encounters that changing pressure, and your eardrum responds by moving back and forth as well. A mechanical movement at the speaker has produced a mechanical movement in your ear without requiring a stream of air to travel from one to the other. This is why sound is often described as a pressure wave when it moves through gases such as air. The phrase may sound technical, but the idea is straightforward. The air becomes slightly more compressed, then slightly less compressed, then more compressed again. These pressure variations spread through the gas. In ordinary conversation, the changes are extremely small. A person does not need to create anything resembling a gust of wind in order to be heard. Your hearing system is sensitive enough to detect remarkably tiny variations in pressure, which is fortunate because dinner conversations would be inconvenient if every sentence required hurricane conditions. It helps to separate two motions that are happening at the same time. There is the motion of the particles in the medium, and there is the motion of the disturbance through the medium. They are not the same. A molecule of air may move a little one way and then another as the sound passes. The wave, however, may continue onward for meters, hundreds of meters, or much farther. This is similar to watching a ripple move across water. The ripple travels across the surface, but a floating leaf usually bobs around rather than being carried across the entire pond at the same speed as the ripple. The pattern moves while much of the material stays roughly where it was. A line of people can give another rough picture. Suppose everyone stands shoulder to shoulder. The person at one end leans gently into the next person, who leans into the next, and so on. A disturbance can move down the line even though nobody walks from one end to the other. If the people are very close and respond quickly, the motion can be passed along efficiently. If they are spaced awkwardly or respond slowly, the disturbance takes longer. Air is obviously not a line of people, and molecules do not politely wait for their turn, but the comparison captures the essential idea that sound is passed onward through local interactions. This immediately brings us closer to the question of speed. If sound travels because one region affects the next, then the speed of sound depends on how quickly those neighbouring regions can influence one another. The source starts the disturbance, but the medium controls how rapidly the disturbance spreads. A loudspeaker does not somehow command the air to carry a note at a certain speed. The air responds according to its own physical properties. That response happens through countless microscopic collisions and forces, and the combined result is the macroscopic wave that moves through the room. There is an important detail here. The molecules that make up air are already moving much faster than the sound wave itself in many ordinary conditions. That can seem puzzling. If the molecules are moving so quickly, why does the sound not simply travel at their speed? The reason is that their motion is random. One molecule may be moving toward the window while another is moving toward the floor, and another toward your cup of tea. Their individual speeds do not create an organized journey in one direction. Sound requires a coordinated pattern of pressure change. The disturbance spreads through the statistical behavior of enormous numbers of particles, rather than by following one particularly enthusiastic molecule across the room. This is also why tracking one molecule would not tell you where the sound is. The molecule might collide with another, change direction, move backward, and later participate in some other part of the motion. The wave is a collective effect. It belongs to the behavior of the medium as a whole rather than to any single particle. That idea appears often in physics. Temperature, pressure, waves, and many other familiar properties describe the combined behavior of huge numbers of microscopic pieces. Sound belongs to that world. It is organized motion emerging from microscopic chaos. Suppose the loudspeaker produces a steady note. Its cone moves forward and backward repeatedly. Each cycle creates another compression and expansion. The distance between similar parts of the repeating pattern is related to the pitch of the sound and the rate at which the source is vibrating. A higher pitched sound involves more rapid changes. A lower pitched sound involves slower changes. Yet both high and low pitched sounds travelling through the same ordinary air move at almost the same overall speed. This is an important point because it shows that the speed of sound is not simply the speed at which the source is vibrating. A violin can play a high note while a large drum produces a low one. but the disturbances from both instruments can cross the same room at essentially the same speed. The difference is in how frequently the pressure rises and falls, not in how fast the overall pattern moves through the air. If the vibrations happen more often, the wave pattern becomes packed differently through space. If they happen less often, the pattern is spread out differently. The medium still determines how rapidly the disturbance itself is transmitted. Loudness is different again. A louder sound generally involves larger pressure variations. The air is being compressed and expanded by a greater amount, within ordinary acoustic limits. That does not mean the loud sound races ahead of the quiet one. If someone whispers while another person speaks loudly from the same distance, both sounds travel through the same air at essentially the same speed. One produces larger pressure changes, but the medium passes both disturbances along according to the same underlying physical rules. A louder voice does not arrive early simply because it is more confident. This distinction between speed, pitch, and loudness helps clear away several common intuitions. We often associate greater energy with greater speed because that happens in many familiar situations. Throw a ball harder and it moves faster. Press an accelerator and a car speeds up. Sound waves do not behave in quite that simple way. Making a sound louder increases the size of the disturbance, but under normal conditions it does not substantially change the characteristic speed at which the pressure wave travels through the air. The speed belongs mainly to the properties of the medium. The relay becomes even more interesting near a boundary. Imagine sound travelling through air toward a closed wooden door. When the pressure disturbance reaches the door, several things can happen. Some of the sound may reflect back into the room. Some of the energy may be absorbed and eventually become tiny amounts of heat. Some of the vibration can enter the wood itself. Once inside the solid material, the disturbance is now being carried by a different medium with different mechanical properties. The vibration may travel through the door and then disturb the air on the other side, producing sound there. This is why closing a door reduces sound without necessarily eliminating it. The wave does not face a simple choice between passing through perfectly or stopping completely. Energy can be divided among reflection, transmission, and absorption. Walls behave similarly. Depending on their thickness, material construction, and the frequency of the sound, some vibrations pass through more readily than others. Deep bass from another room can be particularly persistent because low-frequency vibrations can interact with large structures in ways that make them difficult to block. The music may be 3 rooms away, yet the building itself has joined the performance. Your own hearing depends on several transitions between media. A sound wave arrives through air and pushes on the eardrum. The eardrum vibrates and transfers that motion through tiny bones in the middle ear. Those bones help deliver the vibration into fluid in the inner ear. Inside that fluid, the disturbance creates movements that stimulate specialized sensory cells. These cells convert mechanical activity into electrical signals that the nervous system can use. By the time you experience the sound as a voice or a melody, the disturbance has changed form several times. The ear is therefore not simply a microphone waiting at the end of an airwave. It is a carefully arranged mechanical system designed to transfer vibrations efficiently from one material to another. Air, membrane, bone, fluid, sensory cells, and nerves all participate. The original source may be several meters away, yet the event finally becomes a pattern of activity in your brain. When you hear someone say your name, the air molecules do not carry tiny pieces of language into your head. They carry changing pressure. Your auditory system turns that physical pattern into the experience of speech. The same basic process allows us to recognize complex sounds. A human voice is not one simple vibration. It contains many frequencies at once. Musical instruments create combinations of vibrations that give them their characteristic tone. A violin and a flute can play what we identify as the same musical note, yet they sound different because the detailed mixture of frequencies is different. All of those components can travel together through the air as part of a complicated pressure pattern. Your ear and brain separate and interpret enough of that pattern for you to recognize the source. Remarkably, multiple sounds can occupy the same region of air at the same time. You can hear music while someone speaks, notice rain against the window, and still detect a distant car outside. The waves overlap. The air does not need a separate lane for every sound. Pressure disturbances add together temporarily and then continue. This is one reason sound can form interference patterns where overlapping waves reinforce or reduce one another depending on how their pressure changes line up. Noise-cancelling headphones make practical use of this behaviour. They detect incoming sound and create another sound designed to oppose part of the pressure pattern. When the two disturbances combine appropriately, the pressure variations can partly cancel. The original noise has not been caught and removed like an object. Instead, another organised wave has been introduced so that the combined motion reaching your ear is smaller. It is a clever reminder that sound exists as a pattern in the medium and that patterns can interact. The fact that sound is carried by matter also means the medium itself can be moving. Wind provides an obvious example. If the air has a steady motion relative to the ground, then sound is being carried through air that is itself moving. The speed of the sound relative to the air is still determined by the properties of that air, but an observer standing on the ground can see a different overall result depending on the direction of the wind. This does not mean the wind fundamentally changes how quickly nearby molecules communicate the pressure disturbance. It means the entire medium is drifting while the wave moves through it. The atmosphere is rarely uniform either. Temperature can change with altitude, wind speed can change with height, humidity can vary. Because the speed and direction of sound propagation are influenced by the conditions of the medium, sound waves can bend as they pass through layers of air. They do not always travel along the perfectly straight paths we casually imagine. Under some conditions, sound can curve back toward the ground and be heard surprisingly far from its source. Under others, it may bend away and leave areas where the sound is much weaker. This helps explain some of the odd experiences people have with distant noises. On one evening, a road far away may barely be noticeable. On another, the same traffic seems strangely present. A train can sound much closer than expected. Outdoor music can carry across a surprising distance. The sound source may be behaving exactly as usual. What has changed is the atmosphere through which the relay is taking place. The relay picture becomes even more useful when we move from gases to solids. In air, the pressure wave is transmitted through molecules that are relatively far apart and moving freely between collisions. In a solid, the particles are held much more closely in a structure. They vibrate around positions determined by the forces connecting them to neighbouring particles. Disturb one part of the structure, and those forces produce a response that can be transmitted quickly. This is why placing your ear against a long solid object can allow you to detect vibrations before the same sound arrives through the air. There is an old image of someone placing an ear against a railway track to listen for an approaching train. The basic physics behind the idea is sound. Vibrations from the train can travel efficiently through the steel rail. The same event also produces sound in the surrounding air, but the disturbance in the steel can propagate faster. The rail is not carrying the train noise because its particles are moving along the track. Each region vibrates and passes the mechanical disturbance to the next. Liquids occupy another part of the story. Their particles are close together but are not locked into fixed structural positions in the same way as a solid. Sound still travels very effectively through them, and in water it generally moves much faster than in air. Marine animals make extensive use of this. Whales can communicate over large distances, and dolphins use sound for sophisticated sensing. Human sonar systems also depend on the predictable travel of acoustic waves through water. Once again, the crucial object moving through the environment is the disturbance rather than a parcel of water travelling from source to detector. There is a subtle point worth keeping in mind whenever we use words such as compression and collision. A sound wave in a gas is not simply a row of molecules crashing into one another in a perfectly ordered sequence. The microscopic behaviour is far messier. Molecules are constantly moving in all directions and interacting. The pressure wave is a large-scale description of how the average density and pressure change from region to region. Physics often becomes manageable by moving between these levels of description. We do not need to follow every molecule to understand how the wave behaves, just as we do not need to track every water molecule to describe an ocean wave. That large-scale view also explains why a wave can retain recognizable information over distance. When someone speaks, the motion of their vocal system creates a very complicated sequence of pressure changes. Those variations travel outward. By the time they reach another person, the exact molecules involved are completely different from those near the speaker, but the pressure pattern still contains enough structure for the listener to recognize words. The matter carrying the signal changes continuously, while the information encoded in the disturbance moves onward. In that sense, sound is an extraordinary form of physical copying. One region of matter adopts a pattern of motion because of the region beside it. It then influences another region. The pattern is reproduced again and again as it travels. The copies are not perfect. Energy spreads out, some is absorbed, some reflects from objects, and different frequencies may be affected differently. Eventually the signal can become too weak or distorted to detect. But over useful distances, enough of the pattern survives to carry speech, music, warning calls, echoes, and all the other sounds that fill our lives. This also gives us a more precise way to think about silence. Silence is not the absence of molecular motion. Air in a silent room is still full of molecules racing around. The walls are vibrating thermally. Your body is producing countless microscopic movements. What is missing is a sufficiently organized disturbance within the range your hearing system can detect. Sound is not motion alone, it is structured motion. If you clap your hands, the sudden collision creates a rapid disturbance in the surrounding air. The wave expands outward in many directions. As it spreads, the same energy is distributed across an increasingly large region, which is one reason the sound becomes weaker with distance. Surfaces reflect portions of it. Curtains, furniture, carpets, and people absorb some of it. The room reshapes the sound before it reaches every listener. Yet underneath all that complexity, the fundamental relay remains the same. Local pressure changes produce neighbouring pressure changes, and the disturbance advances. We can now see why the question of speed cannot be separated from the mechanism of transmission. If each step in the relay depends on how strongly the material responds to being disturbed and how much inertia must be moved, then different materials should naturally pass the disturbance at different rates. A material that quickly pushes back when compressed can communicate the change differently from one that gives way easily. A material with greater inertia responds differently from one with less. Temperature alters microscopic motion and therefore changes the behavior of gases. The observed speed is the combined result. This is where the relay race comparison begins to earn its name. No single runner carries the message from the starting line to the finish. Each participant only handles a tiny part of the journey. The speed of the overall message depends on how quickly each handoff can occur. In sound, those handoffs are not deliberate exchanges, but physical responses governed by the forces and motion inside matter. Change the material and you change the nature of the handoff. Make the material more resistant to compression, and the response can become quicker. Change its inertia, and the response changes again. That means our next task is not merely to compare a few memorized speeds in air, water, and steel. The more useful question is what those materials are doing differently. Why does one pass the disturbance rapidly while another is slower? Why does the close packing of a solid not automatically give us the whole answer? Why can two materials with similar densities carry sound at very different speeds? To understand that, we need to look at the two properties that quietly control the relay. How strongly a material resists being deformed, and how much resistance its matter offers to being accelerated. Once we stop thinking of sound as an invisible object moving through space, and start thinking of it as a disturbance being handed through matter, a slightly different question becomes unavoidable. What is the material actually contributing to the journey? The sound source may begin the vibration, but after that first push, the medium has to do nearly everything. The air beside a loudspeaker must respond to the moving surface. The next region of air must respond to the first, the next must respond to that one, and so the disturbance continues outward. If those responses happened more quickly, the sound would travel faster. If they happened more slowly, the sound would travel more slowly. This means that when a sound enters a different material, it is entering a different physical system with different rules for how rapidly one region can influence another. It is tempting to imagine that the speed of sound should depend mainly on how close the particles are together. After all, if particles have to pass a disturbance to their neighbours, then surely putting those neighbours closer together should make the process faster. There is some useful intuition hidden in that idea, but it is not enough on its own. Water is much denser than air, and sound does travel faster through water, which seems to support the simple picture. Steel is denser still and can carry sound faster again. So far, everything looks reassuring. Then you compare different materials more carefully and discover that density alone cannot explain what happens. Some materials can be quite dense and still carry sound more slowly than other materials with lower density. The important question is not simply how much matter is packed into a certain amount of space. We also need to know how that matter responds when it is pushed, squeezed, stretched, or otherwise disturbed. Imagine pressing gently on a soft cushion. The cushion gives way easily. Your hand can move a noticeable distance before the material pushes back strongly. Now, imagine pressing on a solid block of metal. The metal barely changes shape. At the scale of your hand, it seems almost completely rigid. Both materials contain matter, but their response to deformation is very different. One yields readily, while the other strongly resists being changed. That resistance matters enormously for waves. If one part of a material is disturbed, and the material strongly tries to restore its original condition, the effect can be communicated quickly to neighbouring regions. A weaker restoring response generally produces a slower handoff. Air is easy to compress compared with liquids and solids. If you push a piston into a sealed container of air, the gas can be squeezed into a smaller volume. The molecules become more crowded, the pressure rises, and the compressed gas pushes back. Try doing something similar with a container filled completely with water, and the situation changes. Water resists compression much more strongly. Its volume changes only by a very small amount under ordinary pressures. That strong resistance to compression is one important reason sound travels more quickly through water than through air. A pressure disturbance in water produces a strong response, allowing neighbouring regions to affect one another rapidly. This may sound slightly backwards at first. A material that is difficult to compress might seem as though it should slow everything down. In fact, for sound transmission, that resistance is useful. When you squeeze one region of a material, you want that region to push firmly on the next one if the disturbance is going to move quickly. A very compressible material can absorb more of the change locally before producing the same kind of restoring response. A stiffer material passes the mechanical message onward more efficiently. A simple mechanical comparison can help. Imagine a row of objects connected by very soft springs. Push the first object and the spring beside it compresses easily. The first object can move quite a bit before the next object feels a strong push. The disturbance works its way down the row, but the soft connections make the response relatively gentle. Now replace the soft springs with much stiffer ones. Push the first object and its neighbour feels the effect much more strongly and much sooner. The disturbance can move through the system more rapidly because each connection responds more firmly. Real gases, liquids and solids are not rows of balls joined by household springs, of course, but the comparison captures the role of restoring forces. Matter does not need literal metal springs between its particles. Atoms and molecules interact through electromagnetic forces. When their usual spacing is disturbed, those interactions produce forces that tend to resist the change. The details depend on the substance and its physical state, but the broad result is that materials have different levels of stiffness, and that stiffness affects the speed at which mechanical waves can move. If stiffness were the only thing that mattered, however, the story would already be finished, and physics rarely gives up quite that easily. A second property is involved, and that is inertia. Matter resists changes in motion. If you try to accelerate something with more inertia, it responds less readily to the same push. The particles involved in carrying a sound wave therefore do not merely need forces connecting them to their neighbours. They also have mass that must be accelerated back and forth as the wave passes. This creates a balance. Strong restoring forces tend to help a disturbance travel quickly. Greater inertia tends to make the response slower. The speed of sound in a material comes from both effects acting together. That is why simply knowing that one material is denser than another cannot tell you everything. Greater density means there is more mass in a given volume, which can increase the inertia that must respond. But a dense material may also be extremely stiff, and that stiffness can more than compensate. Steel is a good example. It contains far more mass in a given volume than air, but it is also enormously more resistant to deformation. The strong restoring behaviour dominates enough that sound can travel through steel far faster than through the atmosphere. This is one of those places where everyday intuition can be led astray by looking at only one property. We often hear that sound travels faster in solids because their particles are closer together. That explanation is convenient and not entirely useless, but by itself it is incomplete. The spacing between particles is connected to the way materials behave, but closeness alone is not the fundamental reason. What really matters is how strongly a disturbance produces restoring forces, compared with how much inertia has to respond. Two solids can have particles packed closely together and still transmit sound at very different speeds because their internal mechanical properties differ. The same caution applies to gases. Air is a mixture of molecules, and when a sound wave passes through it, small pressure changes create the restoring response. Compress a tiny region, and its pressure becomes slightly greater than the pressure around it. That difference causes the gas to expand outward. The neighbouring region is compressed in turn, and the disturbance advances. How quickly this happens depends on the properties of the gas, including its temperature and the masses of the molecules involved. Suppose we replaced ordinary air with a different gas. The same sound source could produce the same general kind of pressure disturbance, but the wave would not necessarily move at the same speed. A gas made of lighter particles can behave differently from one made of heavier particles under comparable conditions. This is why the speed of sound in helium is significantly greater than in ordinary air. Helium atoms have relatively low mass, and pressure disturbances can propagate through the gas rapidly. Anyone who has heard the familiar high-pitched effect of a voice after inhaling helium has encountered consequences of this change in acoustic conditions, although inhaling gases from pressurized containers is unsafe, and certainly not required for appreciating the physics. The unusual voice produced in helium is often described as though the vocal cords suddenly start vibrating much faster. That is not the main reason for the effect. The vibration rate produced by the vocal cords does not change dramatically simply because the surrounding gas changes. Instead, the resonant behaviour of the vocal tract is altered because sound travels at a different speed through the gas filling it. The frequencies that are emphasised by the mouth and throat shift, changing the character of the voice. The example is useful because it shows that sound speed is not an obscure property, relevant only to laboratories. Change the medium and familiar acoustic systems begin behaving differently. Water provides a less theatrical demonstration. Sound travels through water several times faster than through air because water is far less compressible, despite having much greater density. This matters enormously in the oceans. Marine animals that rely on sound inhabit an environment where acoustic information travels quickly and can cover impressive distances. Human sonar systems use the same basic advantage. A sound pulse is sent through the water, interacts with an object or the sea floor, and some of it returns. The travel time can reveal distance. but only if the properties of the water and the speed of sound through it are understood accurately. Even seawater does not give sound one perfectly fixed speed everywhere. Temperature matters, pressure matters, the amount of dissolved salt matters. Oceanographers have to account for these changes because different layers of the ocean can carry sound differently. As a sound wave moves through regions where its speed changes, its path can bend. Under the right conditions, sound can become guided through broad layers of the ocean and travel enormous distances. What appears at first to be a simple pulse, moving through water, becomes a useful probe of the ocean itself. The atmosphere behaves in a similar way, although the important details differ. Air close to the ground may have one temperature, while air higher above it has another. Wind may change with altitude, humidity may vary. Since sound speed depends on the state of the medium, the wave can encounter slightly different conditions as it travels. Instead of continuing in a perfectly straight line, the direction can gradually change. This bending of sound is called refraction. You may be more familiar with the word from light, such as when a straw appears bent in a glass of water, but waves of many kinds can refract when their speed changes from one region to another. With sound, the effect can make distant noises behave in ways that seem slightly mysterious. On some nights, traffic from far away may sound unexpectedly clear. Voices or music from an outdoor event may carry farther than usual. At other times, a sound can become difficult to hear, even though the source has not changed. The atmosphere is participating in the journey. Temperature is particularly important for sound in air, because it changes how energetically the gas molecules move. Warmer gas contains greater average microscopic motion. When a region is compressed, the pressure response and molecular interactions allow the disturbance to propagate more quickly. Cold air gives a lower sound speed. This does not mean that a warm air molecule literally grabs the sound and runs with it. The molecules are already moving randomly in all directions. Temperature changes the collective response of the gas, and that collective response changes how quickly the organized pressure disturbance spreads. The effect is modest in ordinary life, but it is large enough to matter. Precision measurements involving sound have to take temperature into account. Engineers working with acoustics care about it. Atmospheric scientists care about it. Musicians can even encounter small changes in the behavior of wind instruments, because the speed of sound inside the instrument affects the frequencies at which the air column naturally resonates. A cold instrument and a warmed instrument do not behave in exactly the same way. The fact that sound speed belongs to the medium rather than the source also explains why changing the pitch of a note does not normally make it travel significantly faster through the same air. Suppose two instruments play different notes at the same moment. One produces a low tone and the other produces high tone. The high tone involves more rapid cycles of compression and expansion. The low tone involves fewer cycles during the same amount of time, yet the pressure patterns both move through the same air at nearly the same characteristic speed. The difference appears in the spacing of those patterns. If more cycles are produced during each second while the wave moves at roughly the same speed, the repeating compressions must be closer together. If fewer cycles are produced, they can be farther apart. The medium therefore connects the speed of the wave with the spatial structure of the sound. We do not need an equation to follow the logic. More repetitions happening during the same travel time means those repetitions must fit more closely along the path. This is important for music because a complex sound contains many different frequencies travelling together. If ordinary air caused each audible frequency to move at wildly different speeds, speech and music would become increasingly distorted over distance. The different parts of a word or musical note would separate as they travelled. Fortunately, over the ordinary range of audible frequencies and normal atmospheric conditions, sound speed in air is sufficiently similar that voices and music remain recognizable. Some materials behave in more complicated ways, particularly when we consider different types of mechanical waves. Solids can support forms of vibration that gases cannot. In air, ordinary sound is mainly carried by alternating compression and expansion in the same general direction that the wave travels. A solid can also support disturbances where particles move sideways relative to the direction of propagation. The internal structure of a solid can resist both compression and changes of shape, giving it additional ways to carry mechanical energy. This becomes important when studying vibrations through the Earth. Earthquakes generate several kinds of seismic waves that travel at different speeds because they involve different types of deformation and pass through different materials. Some can move through both solids and liquids. Others require the ability of a solid to resist sideways deformation, and therefore cannot pass through liquid regions in the same way. By studying when these waves arrive at monitoring stations around the world, scientists have learned a remarkable amount about the structure deep inside our planet. The Earth cannot be opened to see what lies thousands of kilometers below our feet, but vibrations can carry information from places we can never visit. The same principle appears on a much smaller scale in medicine and engineering. Ultrasound sends high-frequency sound into the body and detects returning waves. Differences between tissues affect how sound travels and reflects. Engineers can send acoustic waves through structures to investigate hidden flaws. Geologists use waves to study underground layers. In all these cases, sound does more than travel through matter. Its behavior reveals properties of the matter through which it travels. This gives the speed of sound an almost detective-like quality. If you know how quickly a wave should travel through a certain material, measuring its arrival can tell you something about distance. If the speed changes unexpectedly, that change can tell you something about the material itself. Perhaps the temperature is different. Perhaps the composition has changed. Perhaps the wave has entered another layer. A property that seems at first like a simple number becomes a way of asking matter what it is made of and how it behaves. There is another consequence that is easy to overlook. When sound crosses from one medium into another, its speed can change immediately while the rhythm imposed by the original source continues. Imagine a steady sound wave travelling through air and entering water. The source is still vibrating at the same rate. The boundary between air and water does not instruct the source to change its rhythm. But the disturbance can travel at a different speed once it is in the water. Something about the wave must therefore adjust. What changes is the distance between repeating parts of the wave. The vibration rate remains tied to the source, while the speed changes according to the new medium. The wave becomes spatially rearranged. This is another reminder that speed, pitch, and spacing are related but are not the same thing. The medium chooses the speed. The source establishes the rate of vibration. The resulting wave pattern accommodates both. Not all of the sound successfully enters the second medium. At a boundary, some energy is commonly reflected. The amount that passes through depends on how well the mechanical behavior of the two materials matches. This is why interfaces matter so much in acoustics. Sound moving from air into a solid wall experiences a substantial change in conditions. Some of the wave reflects, some enters the wall, and some energy is eventually absorbed. Add soft furnishings, insulation, air gaps, or layers of different materials and the transmission can change considerably. This is part of the reason soundproofing is not simply a matter of using the heaviest object available. Effective control of sound often involves understanding how vibrations move between materials, how structures resonate, where air can leak, and which frequencies are most troublesome. A tiny gap around a door can allow airborne sound through, even if the door itself is heavy. A wall may block voices reasonably well, while low-frequency vibrations find ways to travel through the building structure. The medium keeps deciding what happens at every stage. Even the air inside a room has a say in what you hear beyond merely carrying sound from source to listener. Waves reflect from walls, ceilings, floors, furniture, and other surfaces. Those reflections overlap with newly arriving sound. Certain frequencies may be reinforced in particular locations while others become weaker. This is why a room has its own acoustic character. A bathroom full of hard surfaces produces obvious reflections. A heavily furnished bedroom absorbs more sound and usually feels quieter. A concert hall is designed so that these interactions support the music rather than turning it into a confused mixture of delayed reflections. In every case, the sound source supplies the initial disturbance, but the environment shapes what follows. The medium determines how quickly the disturbance propagates. Boundaries determine how much reflects or passes through. Geometry determines where waves meet. Absorption gradually removes organized mechanical energy and turns part of it into microscopic thermal motion. By the time the sound reaches a listener, it carries a record not only of its source, but also of the journey. That journey can be surprisingly sensitive to small changes in conditions. The same distant bell may sound slightly different on a cold morning than on a warm afternoon. A noise across water may carry farther than expected. A knock transmitted through a solid surface may reach you before the airborne version. None of these effects require sound itself to change its fundamental identity. The medium has changed, and because sound is inseparable from its medium, the result changes with it. This gives us a much stronger answer to the question of where sound gets its speed. It gets that speed from the mechanical response of matter. A disturbance compresses or deforms part of a material. The material pushes back. That response affects neighbouring matter. Inertia resists the acceleration. The competition between restoring behaviour and inertia determines how rapidly the disturbance can advance. Temperature, composition, pressure, and physical state can all influence those properties, so they can influence the speed as well. Once those two competing tendencies are recognised, a pattern begins to appear across gases, liquids, and solids. The fastest medium is not simply the one with the lightest particles, nor the one with the greatest density, nor the one whose particles happen to sit closest together. What matters is the relationship between how strongly the material reacts when disturbed and how difficult its matter is to accelerate. That relationship is why a soft material and a rigid material can behave so differently, why water outruns air despite being denser, and why some solids can send vibrations racing ahead of both. The next step is to look more closely at those two properties themselves, because they are doing nearly all of the hidden work. One tells us how strongly matter pushes back when we try to deform it. The other tells us how reluctant that matter is to change its motion. Put them together, and the apparently arbitrary speed of sound begins to emerge from something much more understandable. The simple fact that matter can resist being changed, but can never respond without having to move. The two properties we have been circling around can be understood without turning this into a mathematics lesson. One tells us how strongly a material resists being squeezed or stretched. The other tells us how much matter has to be moved when that response happens. Put those together and the speed of sound begins to make much more sense. A pressure disturbance does not move through a material simply because particles happen to be close to one another. It moves because one region is disturbed. That disturbance produces a restoring force, and the restoring force accelerates neighbouring matter. Every tiny step in the journey depends on how forcefully the material reacts and how difficult its particles are to move. You can think of this as a contest between springiness and weight, although physicists use more precise language when they measure these properties. Springiness encourages a quick response. Inertia slows the response down. Sound travels at the pace that emerges from the competition between them. Consider a soft foam cushion and a steel bar. Push your hand into the cushion and the material changes shape easily. You can compress quite a large region before the cushion pushes back strongly enough to stop you. Press on the steel bar with the same effort and almost nothing visible happens. The atoms in the steel move slightly, but the structure strongly resists being deformed. That difference matters to a sound wave. When one region of steel is pushed away from its normal condition, neighbouring regions feel a strong restoring influence. The material is eager, in a mechanical sense, to return toward its original arrangement. The disturbance therefore gets passed onward very efficiently. In a softer material, the same amount of deformation produces a weaker restoring response, so the handoff can be slower. The word springiness can be slightly misleading, because a material does not need to feel springy in your hand. Steel does not behave like a rubber band when you pick it up, yet at very small scales it has elastic behaviour. If you deform it slightly and stay within its normal elastic limits, internal forces try to restore its previous shape. Rock does this, glass does this, wood does it. Water has its own resistance to compression, and even air pushes back when it's squeezed. The details differ enormously, but the basic idea is common. Matter has preferred arrangements and conditions. Disturb those conditions and forces appear that tend to oppose the disturbance. Air gives us an especially clear example because we can compress it easily. Imagine a sealed cylinder with a movable piston at one end. Push the piston inward and the gas occupies less space. The molecules become more crowded, so the pressure rises. If you release the piston, the compressed gas can push it outward again. There is our restoring behaviour. A region of compressed air does not simply remain compressed while the rest of the gas ignores it. The pressure difference causes the gas to expand toward regions of lower pressure. During a sound wave, this happens on a tiny scale again and again. Compression creates a pressure increase. That pressure increase pushes on neighbouring air. The neighbour becomes compressed and pushes on the region beyond it. The sound continues. Now imagine a material that offered almost no resistance when compressed. You could push one region inward, and it would simply accept the change without strongly affecting its neighbours. A disturbance would have difficulty spreading quickly, because the local deformation would not produce much restoring force. At the opposite extreme, imagine a material that resisted compression very strongly. Even a tiny displacement would create a significant response, and that response would immediately influence nearby matter. Other things being equal, the second material would transmit pressure disturbances more quickly. Other things, unfortunately for anyone hoping physics will remain simple, are rarely equal. The material also has inertia. When a sound wave passes, particles have to accelerate away from their usual motion and then change direction. They do not travel with the sound for long distances, but they do participate in the local vibration. Moving them requires force. The more inertia involved, the more difficult it is to produce a rapid response. This is the same basic reason an empty shopping trolley is easier to accelerate than a heavily loaded one. Give both the same push, and the lighter trolley changes its motion more readily. The loaded trolley has more inertia and responds more slowly. At the microscopic level, the same general principle matters for sound. Strong restoring forces help neighbouring regions react rapidly, while greater inertia makes them harder to accelerate. Sound speed, therefore, cannot be predicted just by asking whether a material is heavy or light. Nor can it be predicted by asking only whether the material is stiff or soft. We need both pieces of information. This explains why the simple claim that sound travels faster in solids because their particles are closer together is not quite enough. It is a useful first picture, and it points in roughly the right direction for many familiar materials, but particle spacing alone cannot tell us the speed. Imagine two materials whose particles are both packed closely together. One has very strong internal restoring forces, the other deforms much more easily. A disturbance will not necessarily travel through them at the same rate. The arrangement of the particles matters, the forces between them matter, and the amount of inertia that must respond matters. Steel demonstrates this nicely. Steel is far denser than air, so there is much more mass packed into a given amount of space. If density alone controlled sound speed, we might expect all that extra inertia to make sound crawl through steel. Instead, sound generally travels much faster through steel than through air. The reason is that steel is enormously stiffer. Its internal structure responds so strongly to small deformations that the disturbance can be passed onward very rapidly, despite the greater amount of matter involved. Rubber gives us a different comparison. Rubber is a solid, and its particles are certainly far closer together than the molecules in air, but rubber can deform much more easily than steel. Its internal mechanical response is different. Simply labeling both materials as solids tells us very little about the exact speed of sound through them. The category is useful, but the material properties provide the real explanation. Water sits between the familiar worlds of gases and rigid solids. It is much denser than air, which gives it greater inertia, yet it is also dramatically harder to compress. That resistance to compression is strong enough that sound travels much faster through water than through the atmosphere. This is why underwater acoustics behave so differently from everyday hearing. A pressure disturbance can spread through the liquid with impressive speed because the water strongly resists being squeezed into a smaller volume. If you have ever tried to compress air in a bicycle pump with the outlet blocked, you can feel the gas giving way as the pressure rises. The volume changes noticeably. Water would be far less cooperative. Under everyday conditions, trying to squeeze water into a significantly smaller volume is extremely difficult. That reluctance to compress means that a small pressure disturbance creates a strong response, and that response helps transmit sound rapidly. The comparison between air and water also reveals why density sometimes confuses explanations of sound. Water contains far more mass in the same amount of space, and that should make acceleration harder. It does. But the much greater resistance to compression pushes the speed in the opposite direction, and that effect wins strongly enough for sound to move faster in water. Nature is balancing both properties at once. Looking at either one separately gives only half the story. Gases offer another interesting case because their stiffness is connected closely to pressure and temperature. A gas does not have a rigid structure like a solid. Its molecules move freely and spend much of their time separated from one another. Yet the gas still resists compression. Crowd the molecules into a smaller region, and collisions with the surrounding boundaries become more frequent and energetic, producing greater pressure. A compressed region therefore pushes outward. Temperature changes this behavior because temperature is related to microscopic motion. In a warmer gas, the particles have greater average kinetic energy. They move more energetically, and the relationship between pressure, compression, and motion changes in a way that allows sound disturbances to propagate more quickly. This is why warm air gives sound a greater speed than cold air. We will look much more closely at temperature later, but for now it is useful to see that even the springiness of a gas is not a fixed quality. Change the state of the gas and you change the way it responds. The composition of the gas matters as well. Ordinary air is mostly nitrogen and oxygen, along with smaller amounts of other gases. Replace that mixture with a gas whose particles have substantially different masses, and sound can travel at a different speed, even when the temperature is similar. Helium provides the famous example. Sound moves much faster through helium than through ordinary air. The effect reflects the different microscopic properties of the gas, including the relatively low mass of helium atoms. This difference has an amusing consequence for the human voice. When people hear the unusual voice associated with helium, they often assume the vocal cords must suddenly be producing a much higher fundamental pitch. The main effect is actually more complicated. The vocal cords still provide the basic vibration, but your mouth and throat act as resonating spaces that emphasize certain parts of the sound. Changing the gas changes the speed of sound inside those spaces, which shifts their resonances and alters the character of the voice. The result sounds dramatically higher and thinner, even though the source vibration has not simply been multiplied in the way people often imagine. It is a nice example of a medium changing acoustics, without the speaker consciously doing anything different. The relationship between stiffness and inertia also helps explain why sound can travel at different speeds within different parts of the human body. Bone, muscle, fat, blood, and other tissues have different densities and mechanical properties. Medical ultrasound depends on these differences. High-frequency sound is sent to the body, and as the wave encounters boundaries between tissues, part of the energy can be reflected while part continues onward. By measuring the returning signals, an ultrasound system can build information about internal structures. For this to work accurately, the system must account for how sound behaves in biological materials. Doctors are not the only people who use sound as a probe. Engineers can send acoustic or ultrasonic waves through metal components to look for cracks or hidden defects. If a wave encounters a boundary where the material changes unexpectedly, part of the disturbance can reflect. By studying those reflections, engineers can detect problems without cutting the object open. The technique works because sound is sensitive to mechanical properties. A wave passing through matter is constantly responding to what the material allows. Geologists use the same broad principle on a much larger scale. Earthquakes produce mechanical waves that travel through the planet. Different waves respond differently to the properties of rock and liquid deep underground. By comparing when those waves arrive at monitoring stations, scientists can infer information about regions that no human has ever visited. We know important things about the interior structure of Earth, partly because the planet rings after an earthquake and the vibrations reveal what they travelled through. Solids make this especially interesting because they can resist more than simple compression. A fluid can push back against being squeezed, but it cannot maintain the same kind of resistance to sideways deformation that a solid can. If you push the top of a solid block sideways while holding the bottom in place, the material resists the change of shape. That gives solids additional ways to carry waves. Some disturbances involve compression, others involve sideways motion. Because these motions depend on different mechanical properties, they can travel at different speeds even through the same material. This is why there is not always a single number that completely describes sound or mechanical wave speed in a solid. The type of disturbance matters. A wave involving compression can move at one characteristic speed, while another kind involving sideways deformation moves differently. For everyday listening, we rarely need to worry about this distinction, because sound in the air around us is dominated by pressure variations. For seismology and material science, however, the distinction becomes extremely useful. You can get a rough physical feeling for the importance of restoring force with a spring. Attach a weight to a soft spring, pull it slightly and release it. The weight moves back and forth at a certain pace. Replace the spring with a stiffer one while keeping the same weight, and the motion becomes quicker. The stronger restoring force changes the response. Now keep the spring but replace the weight with something much heavier. The oscillation becomes slower because more inertia must be accelerated. Although sound travelling through a continuous material is more complicated than a single weight on a spring, the same two ingredients appear again. Stiffness encourages rapid change. Inertia opposes it. At the atomic scale, a solid can be pictured very loosely as particles connected by effective springs. That is not a literal model of tiny metal coils sitting between atoms, but it is a useful way to imagine how small displacements create restoring forces. Move an atom slightly closer to its neighbour, and the interaction changes. Pull it slightly farther away, and the interaction changes again. The atoms tend to vibrate around stable positions. A disturbance can therefore propagate as one atom influences the next. If the effective connections are strong, the disturbance can move rapidly. If the atoms are especially massive, their inertia can slow the response. Different combinations produce different sound speeds. Diamond, for example, is famous for being extremely stiff because of the strong bonding in its crystal structure. Mechanical disturbances can travel through it extremely quickly. Lead, despite being very dense, has different elastic properties and does not transmit sound at anything like the same speed. Once again, density alone refuses to give us the answer. Wood adds another complication because some materials are not mechanically identical in every direction. A tree grows with a structure. Fibres tend to run along the grain, and the material responds differently depending on whether a disturbance moves along those fibres or across them. Sound can therefore travel at different speeds in different directions through the same piece of wood. Anyone designing musical instruments cares deeply about this behaviour. The wood in a violin, guitar, piano, or other instrument is not merely decorative. Its internal structure affects how vibrations spread and which motions are reinforced. Crystal structures can show similar direction-dependent behavior. In some materials, the arrangement of atoms makes the stiffness different depending on the direction in which the material is disturbed. A sound wave travelling one way can therefore have a different speed from a wave travelling another way through the same crystal. This might seem strange if we're used to thinking of a material as having one fixed list of properties, but matter can be more organised than that. Direction can matter. Pressure can also change sound speed because pressure can change the physical state and density of a medium. Deep in the ocean, for example, water is under far greater pressure than at the surface. Temperature and salinity also vary with depth. Together, these properties cause the speed of sound to change throughout the water column. A sound wave moving through the ocean can encounter regions where its speed gradually increases or decreases, and that causes its path to bend. This bending matters enormously for underwater communication. Sound can become trapped in regions where the changing speed repeatedly bends the wave back toward a particular depth. In the ocean, such conditions can create natural sound channels that allow low-frequency noises to travel surprisingly large distances. Whales can take advantage of the acoustic properties of seawater, and naval sonar systems have long had to understand them. The ocean is not merely a large tank of uniform water, it is a layered acoustic environment. The same underlying physics appears in the atmosphere, where temperature often plays the dominant role. If sound moves through layers of air with different sound speeds, the wave can bend toward the region where it travels more slowly. The exact result depends on the temperature pattern and wind conditions. On some nights, air close to the ground can be cooler than air above it. Sound that would otherwise spread upward may curve back toward the surface, allowing distant noises to be heard more clearly. This is why a highway, train or industrial site can occasionally seem much louder at night, even though nothing at the source has changed. The medium is making decisions at every stage, although not conscious ones. Its stiffness determines how strongly it reacts. Its density contributes inertia. Its temperature influences microscopic motion. Its composition determines what kinds of particles are involved. Its structure may change the response with direction. Pressure can alter its state. Boundaries can reflect part of the wave and transmit the rest. Sound is completely dependent on this collection of material properties. That dependence also explains something important about the word speed. The speed of sound is the speed at which a small disturbance can propagate through the medium. It is not necessarily the speed at which the material itself is flowing. Air can have wind, water can have currents. A sound wave moves relative to that moving medium while the medium itself may be travelling relative to the ground. Imagine standing beside a river and dropping a small floating object into the water. The object can move relative to the water while the entire water mass is also moving downstream. Sound in wind involves a related distinction. The wave has a characteristic propagation speed through the air, while the air itself can carry the whole pattern along. This becomes especially important when we later discuss aircraft. An aircraft does not care only about its speed relative to the ground. What matters for the formation of shock waves is how fast it moves relative to the surrounding air, compared with how quickly pressure disturbances can spread through that air. The local speed of sound depends on the atmospheric conditions. That is why pilots and engineers use a comparison with the local sound speed, rather than treating one number as a universal boundary everywhere. It also tells us why the phrase sound barrier can be misleading. There is no fixed wall in nature located at a particular speed. An aircraft approaching the local speed of sound is catching up with the pressure disturbances it creates in the surrounding air. Those disturbances normally run ahead and tell the air farther forward that something is coming. As the aircraft moves faster, that warning has less time to spread. Near the sound speed, pressure changes begin interacting in much more dramatic ways. The behaviour follows directly from the same properties we have been discussing. The air can only communicate mechanical information so quickly, because its stiffness and inertia set the pace. The most important thing to keep is that sound speed is not arbitrary. Nature is not assigning a number to each material from a mysterious list. The speed emerges from the material response. Squeeze a region and it pushes back. That push accelerates neighbouring matter. The neighbouring region then pushes farther onward. A stronger restoring response tends to make each handoff quicker. Greater inertia tends to make each handoff slower. Different materials balance those effects differently, and the result is the speed at which a pressure disturbance can travel. This is why simply looking at how closely particles are packed can never give the complete answer. Water is much denser than air, yet carries sound faster because it resists compression so strongly. Steel is much denser still, but also far stiffer, so disturbances move faster again. Different solids depart from that simple ranking because their elastic properties differ. Gases change with temperature because their restoring behaviour is linked to microscopic molecular motion. Everything returns to how matter responds when pushed. And now that the hidden competition between springiness and inertia is clearer, we can make the comparison much more concrete. Instead of speaking generally about solids, liquids, and gases, we can place familiar materials side by side and ask what sound actually does inside them. Air, water, steel, wood, glass, and other substances give the same disturbance very different travel times, and those differences show just how much control the medium has over every sound that passes through it. Now that we know sound depends on both the restoring strength of a material and the inertia of the matter being moved, we can finally compare some familiar substances and see what those ideas look like in practice. Air, water, and steel are useful because they seem so different in everyday life. Air feels almost like nothing. Water has weight and pushes back when we move through it. Steel feels solid, heavy, and almost completely unwilling to change shape. Yet all three can carry sound, and they do so at very different speeds. A sound disturbance moves through ordinary air relatively slowly, travels several times faster through water, and can move faster still through steel. The reason is not simply that the particles become more closely packed as we move from gas to liquid to solid. That description points us in the right direction, but the real explanation is found in how strongly each material reacts when compressed, and how much inertia must respond to that reaction. Air is where most of our experience with sound begins. Conversations, music, footsteps, birds, traffic, alarms, and the suspicious noise from the kitchen that you were certain was nothing until it happened again all reach us mainly through the atmosphere. Air seems almost effortless to disturb. Wave your hand and it moves aside. Blow into a balloon and the gas compresses enough to fit inside. Push down on a bicycle pump with the outlet blocked and you can feel the trapped air giving way as its pressure increases. Air does resist compression, but compared with liquids and solids, it is very flexible. That matters because a sound wave relies on the pressure created when one region is squeezed. The stronger the pressure response, the more quickly the disturbance can push into the neighbouring region. When a loudspeaker moves forward, the air directly in front of it becomes slightly compressed. That region then pushes on the air farther ahead. Because air is relatively easy to compress, some of the motion goes into changing the spacing between molecules before a strong restoring pressure develops. The disturbance still moves quickly by human standards, but the mechanical response is comparatively gentle. The gas molecules also have inertia, so they need time to accelerate and reverse their local motion as the pressure wave passes. The familiar speed of sound in air emerges from this balance. If you could slow the process down enough to watch it, you would not see a tidy line of molecules waiting to be pushed one after another. Air is far too restless for that. Molecules are moving randomly in every direction, colliding constantly. The sound wave appears as a small organised change layered on top of all that microscopic activity. A region has slightly greater pressure than average, followed by one with slightly lower pressure, and those variations move through the gas. The individual molecular motion is chaotic, but the large-scale disturbance has order. The situation changes dramatically when sound enters water. Water is much denser than air, so there is considerably more matter packed into the same volume. At first, that might sound like bad news for the wave. More matter means more inertia. If inertia resists acceleration, surely water should slow the sound down. But water also has a property that matters even more strongly. It is remarkably difficult to compress. You can experience this difference without any special equipment. Trap some air inside a sealed plastic syringe and press on the plunger. The gas volume decreases noticeably. Fill the same kind of sealed space completely with water, and the plunger becomes much harder to move. The liquid will not surrender much volume under ordinary pressure. Water molecules are already close together, and pushing them significantly closer requires a strong force. That means a small compression creates a strong pressure response. For a sound wave, this strong response is extremely useful. Disturb one region of water, and it pushes firmly on the region beside it. That neighbouring water responds and passes the pressure change onward. Although the greater density gives the system more inertia than air, the enormous increase in resistance to compression more than compensates. The result is that sound travels several times faster through water than it does through the atmosphere. This difference becomes noticeable in the way the underwater world uses sound. Light does not always travel conveniently through the ocean. Water can become dark quickly, especially at depth, and particles can reduce visibility even when sunlight is available. Sound, however, can travel over very large distances under the right conditions. For many marine animals, hearing is therefore far more than an additional sense. It can become one of the main ways of understanding the environment. Whales use low-frequency calls that can travel extraordinary distances through seawater. Dolphins use much higher frequency sounds for echolocation, producing clicks and listening to the returning echoes. From those echoes, they can gather information about objects around them. Human sonar operates on the same broad principle. A sound pulse travels through the water, reflects from an object, a submarine, a school of fish, or the seafloor, and part of it returns to a receiver. The time taken for the journey can reveal how far away the reflecting object is. To make such measurements accurately, knowing that sound is faster in water is not enough. The speed itself changes with the condition of the ocean. Seawater is not identical everywhere. Temperature changes with depth and location. Pressure increases as we descend. The amount of dissolved salt varies. Each of these can influence how sound travels. Oceanographers therefore pay careful attention to the acoustic structure of the water. A particularly interesting effect occurs because sound waves bend when their speed changes gradually from one region to another. Instead of travelling forever along a perfectly straight path, a wave can curve. In parts of the ocean, changes in temperature and pressure create layers where sound is repeatedly bent back toward a certain depth. This can form a natural acoustic pathway, in which sound travels unusually far without escaping quickly toward the surface or deep sea floor. The ocean, in other words, can behave like a vast sound guide. A noise produced in one place may reach a distant receiver by following paths shaped by temperature, pressure, and salinity. The water is not merely an empty stage through which sound happens to pass. Its physical state determines the route and speed of the signal at every point. Steel takes the comparison in another direction. A steel object contains much more mass in a given volume than either air or water. Its inertia is substantial. Yet sound can travel through steel extraordinarily quickly because the material is also extremely stiff. Disturb one region of steel and strong internal forces act to restore the structure. Neighbouring atoms respond quickly and the mechanical disturbance moves onward with impressive speed. You can experience the effectiveness of solids as sound carriers in very ordinary situations. Place an ear against a wooden table while somebody taps the far end, and the impact may become clearer than it was through the air. Put your ear against a wall, and noises from another room can become easier to detect. A person walking upstairs can transmit vibrations through floorboards, beams, walls, and ceilings, sometimes with such efficiency that the footsteps seem to come from everywhere at once. Steel can take this effect further. The old practice of listening along a railway track relied on the fact that vibrations from an approaching train can travel rapidly through the metal. The disturbance moving through the rail may arrive before the sound travelling through the surrounding air. The train creates vibrations in both media, but the two routes do not transmit them at the same speed. Nothing inside the rail needs to move from the train all the way to the listener. The atoms vibrate around their local positions. Their interactions pass the disturbance through the structure. Because those interactions provide a strong restoring response, the wave can move quickly, even though the material itself is dense and heavy. It is worth being careful with the word stiff, because everyday language can make it sound like stiffness, and hardness are the same thing. They are related in some circumstances, but describe different aspects of material behaviour. A material can resist scratching, yet respond differently to stretching or compression. For sound, the important question is how the material responds to the particular deformation involved in the wave. This is why two solids can have very different sound speeds. Simply knowing that something is solid does not tell us enough. Steel, glass, wood, rubber, stone and diamond all have particles packed closely together, but their internal structures and restoring forces differ enormously. Sound responds to those differences. Rubber is a useful reminder. It is clearly a solid, yet we can stretch and deform it far more easily than steel. Its response to a mechanical disturbance is therefore very different. A wave moving through rubber does not receive the same rapid restoring reaction that it would experience in a much stiffer solid. Calling both substances solids hides the details that matter most. Diamond offers almost the opposite example. The atoms in diamond are linked through an extremely strong structure, giving the material exceptional stiffness. Mechanical disturbances can propagate through it at very high speeds. The atoms themselves are not racing across the diamond. Their local interactions are simply capable of transmitting changes rapidly. Wood introduces yet another complication. Unlike a uniform block of an idealized material, wood has a grain produced by the biological structure of a tree. Its fibers tend to run in preferred directions. As a result, vibrations can travel differently along the grain than across it. The same piece of wood may therefore carry sound at different speeds depending on the direction of travel. Musical instrument makers have been working with this reality for centuries, often long before the microscopic physics was understood. The choice of wood in a violin, guitar, piano, or other acoustic instrument is not merely about appearance. The way the material vibrates influences how energy from strings or other sources is distributed. Different pieces of wood can respond differently even when they come from the same species because growth, density, grain, moisture, and construction all matter. A guitar gives a convenient example of why material behavior matters so much. Pluck a string by itself and it does not move much air. Connect that string to the body of the instrument and the vibration can be transferred into a much larger structure. The wooden surfaces move and push on the surrounding air, allowing the sound to radiate more effectively. Vibrations travel through the instrument before becoming airborne sound that reaches the listener. A piano uses a similar trick on a larger scale. The strings vibrate, but the soundboard plays a major role in communicating that vibration to the air. The mechanical properties of the materials influence how different frequencies are supported, how long they persist, and how strongly they radiate. What we hear as the character of an instrument is partly the result of waves repeatedly changing media. That transfer from one material to another introduces another important piece of the story. Sound does not always pass cleanly through a boundary. When a wave travelling in air reaches a wall, some of its energy reflects. Some may enter the wall, some is absorbed. The amount that successfully crosses depends on how the two media respond mechanically. You can hear this immediately in a house. Close a door and a conversation outside becomes quieter, but usually not silent. Some airborne sound reflects from the door. Some makes the door vibrate. That vibration can create new sound in the air on the other side. Other parts of the sound may travel through the walls, floor or ceiling instead. Low-frequency sounds are particularly skilled at finding inconvenient routes through buildings. Deep bass can vibrate large surfaces and structural elements, allowing energy to travel through floors and walls. This is why a distant television or music system may become an indistinct thumping even when higher voices are difficult to hear. The building has filtered the original sound according to how its materials respond. Engineers designing quiet rooms have to consider all of these pathways. Making a wall thick can help, but thickness alone does not solve every problem. Vibrations can travel through beams and frames. Gaps around doors can leak airborne sound. Ventilation ducts can provide routes between rooms. Different layers can reflect, absorb, or transmit different frequencies. Controlling sound often becomes a problem of controlling how energy moves through several connected materials. The same ideas explain why you hear your own voice differently from everyone else. When you speak, sound reaches your ears through air, but vibrations also travel through the bones and tissues of your head. Bone carries these mechanical disturbances differently from air. The combined result is the familiar voice you have heard throughout your life. A recording removes much of that internal route. When the recording plays back, the sound reaches you mainly through the surrounding air, just as your voice reaches another person. The result can seem oddly unfamiliar, sometimes enough to make people suspect that the microphone has committed some kind of personal betrayal. The recording is usually not inventing a new voice. You're simply hearing your own speech through a different collection of media. Our ears themselves depend on carefully managed transitions between substances. Sound begins in air and moves the eardrum. That vibration is passed through tiny bones. The motion is then transferred into fluid inside the inner ear. Each stage involves a change in mechanical conditions. The anatomy of the ear helps make those transfers effective enough for extremely small pressure variations in the atmosphere to become detectable movement inside the auditory system. The contrast between air, water, and solids also matters enormously in medicine. Ultrasound imaging sends high-frequency mechanical waves into the body. Human tissue contains solids and liquids with different acoustic properties. When the wave reaches a boundary between tissues, part of it can reflect. The returning signals contain information about where those boundaries are. A scanner can build an image because sound reacts to the materials it encounters. The machine is not seeing directly in the way a camera does. It is listening to echoes produced inside the body. The timing and strength of those echoes reveal structure. A layer of gel is usually placed between an ultrasound probe and the skin for the same reason boundaries matter elsewhere. Air between the probe and the body would create a poor acoustic connection. Because air and tissue have very different mechanical properties, the gel helps remove the air gap and allows more of the sound energy to enter the body. A small amount of transparent gel is therefore doing something surprisingly important. It is creating a better bridge between two acoustic systems. Industry uses similar techniques to inspect materials without cutting them apart. High-frequency sound can be sent through metal, and hidden cracks or defects can produce reflections. Engineers analyze the returning waves to determine whether something unusual lies inside. Aircraft components, pipelines, welds, and other structures can be examined this way. The technique works because a mechanical wave notices changes in its environment. A crack may introduce an air gap or a boundary with very different properties. The sound responds, and that response can be detected. A flaw hidden from ordinary sight can reveal itself through the way it interrupts the journey of a vibration. Earthquakes provide the largest version of the same idea available to us. When rock suddenly shifts underground, enormous mechanical disturbances spread through the planet. Different kinds of seismic waves travel at different speeds and respond differently to solids and liquids. Monitoring stations around the world record when those waves arrive. From these arrival patterns, scientists can infer the structure deep inside Earth. Some waves pass through regions that others cannot. Their paths bend as the properties of the material change. The planet becomes a gigantic object being investigated with vibrations, rather like an acoustic scan on an impossible scale. What makes all these examples useful is that the wave carries information about the medium, as well as about the source. If you know when a sound was produced and measure when it arrives, the travel time can tell you about distance. If you know the distance and measure the travel time, you can learn something about the speed. If the speed differs from what you expected, the material may be telling you that its temperature, composition, pressure, or structure is different. Even a simple echo contains this kind of information. Call toward a cliff, and the returning sound tells you that a reflecting surface exists somewhere ahead. Measure the delay accurately and, if you know the local speed of sound, you can estimate the distance. Bats perform a far more sophisticated biological version of this process, producing calls and interpreting echoes from nearby objects. For a bat flying through darkness, the timing of reflected sound helps reveal the position of obstacles and prey. The echoes may return only moments apart, yet the nervous system can extract useful spatial information from them. Dolphins accomplish a comparable task underwater, although the speed of sound and the behaviour of the medium are different. This difference in sound speed between air and water means that an echolocation system designed for one environment cannot simply behave identically in the other. The same travel time corresponds to a different distance depending on the medium. Once again, the material sets the rules. The importance of the medium becomes even clearer if we imagine a sound crossing several materials during one journey. Suppose someone taps a metal pipe running through a wall. The initial disturbance travels through the metal. Some energy passes into the wall where the pipe is attached. Some enters the air around it. At another location, the vibrating pipe may disturb the air again, creating a sound you can hear. The noise arriving at your ear may therefore have followed several routes, each with a different speed. One portion travelled mainly through air. Another moved through metal and structural material before becoming airborne near you. Because the paths and speeds differ, the signals may arrive at slightly different times and with different strengths. In a complicated building, sound can become a collection of journeys rather than one simple path. Concert halls are designed with these journeys in mind. The direct sound from a performer reaches the audience first. Reflected sound follows from the walls, ceiling, and other surfaces. If the reflections arrive at useful times, they can add richness and a sense of space. If they arrive too strongly or too late, speech becomes difficult to understand and music can lose clarity. The choice of materials matters because surfaces do not all reflect sound equally. Heavy, hard surfaces can produce strong reflections. Soft, porous materials can absorb more energy. Seats, curtains, panels, carpets, and even the audience influence the acoustic environment. An empty hall can sound noticeably different from the same hall filled with people, because human bodies and clothing absorb sound. In every case, the material is doing more than allowing sound to pass. It determines speed, reflection, absorption, and transmission. The same physical disturbance can behave very differently depending on where it goes. This is why the simple ranking of air, water, and steel is useful, but should not become a rigid rule that gases are always slow, liquids always faster, and solids always fastest. Many familiar examples follow that pattern, but the underlying physics does not care about our categories. It cares about actual mechanical properties. A particularly stiff material can carry disturbances rapidly. A soft solid may be slower. Different liquids can have different responses. Different gases can produce very different sound speeds. Helium makes this obvious among gases. Because of its microscopic properties, sound travels much faster through helium than through ordinary air. Other gases behave differently again. The label gas tells us the broad state of matter, but not the exact result. Temperature complicates the picture even within the same gas. Take ordinary air and warm it, and sound travels faster. Cool it, and sound slows down. Nothing has changed from gas to liquid or from liquid to solid. The chemical mixture may remain almost the same, yet the speed shifts because the microscopic motion and pressure response of the air have changed. That means the atmosphere around you does not provide one perfectly fixed sound speed every day of the year. A freezing winter morning and a warm summer afternoon offer slightly different acoustic conditions. The difference is usually too small to notice during ordinary conversation, but it becomes important over long distances and in precise measurements. It can also affect the route that sound follows. If the air near the ground has a different temperature from the air above, different parts of the wave can travel at slightly different speeds. The wave bends as a result. Combine that with wind, which may also change with altitude, and the atmosphere can guide sound in surprisingly complicated ways. This brings us from the broad comparison of materials to something much closer to everyday experience. We do not normally replace the air around us with water or steel, but the temperature of the atmosphere changes constantly. Morning becomes afternoon, seasons turn. Warm air rises and cool air settles. Layers form above the ground. The very medium carrying every voice, footstep, bird call and distant engine is continually changing its acoustic behaviour, which means the next useful question is not why sound differs between completely different materials, but why the same air can change the speed of sound simply by becoming warmer or colder. The air around us is constantly changing, even when it appears perfectly still. A room can warm slowly after sunrise. A street cools after the sun disappears behind the buildings. Warm air collects near a ceiling while cooler air remains closer to the floor. Outdoors, the ground can heat the air above it during the day and lose that heat again after sunset. None of this looks especially dramatic, but for sound it matters. The same voice, bell, engine, or clap can travel through the same collection of gases at a slightly different speed simply because the temperature has changed. Warm air allows sound to move faster than cold air, and the reason takes us back to the microscopic motion that has been quietly carrying every sound we have discussed. Temperature can seem like a property added to matter from the outside, something we measure by touching an object or looking at a thermometer. At the molecular level, however, temperature is closely connected with motion. The molecules in a gas are constantly moving. They race through the available space, collide with other molecules, strike surfaces, change direction, and continue. Warm a gas, and on average, that microscopic motion becomes more energetic. Cool the gas, and the average motion becomes less energetic. The individual molecules still have a wide range of speeds, so it would be misleading to imagine that every molecule in warm air moves at one particular pace, while every molecule in cold air moves at another. What changes is the overall distribution of molecular motion. That matters because sound in air is a pressure disturbance, and pressure depends on what those molecules are doing. When a loudspeaker pushes forward, it crowds the nearby air slightly. Molecules in that region interact with the surrounding gas and create a pressure response. The disturbance is passed onward because one region can influence the next. In warmer air, the molecules involved are already moving more energetically, so changes in pressure are communicated through the gas more rapidly. The relay we have been following becomes quicker. There is a subtle distinction worth keeping clear here. Sound does not travel faster in warm air because one particular warm molecule grabs the wave and rushes across the room with it. Individual gas molecules are moving randomly, often at speeds greater than the sound wave itself, and they constantly change direction. What matters is how quickly an organised pressure disturbance can propagate through the entire collection. Temperature changes the statistical behaviour of the gas, and the sound speed changes with it. Imagine two identical rooms filled with ordinary air. One is very cold, and the other comfortably warm. In each room, a loudspeaker produces the same short click. The source behaves the same way in both places. It pushes on the nearby gas and begins a pressure disturbance. In the warmer room, that disturbance reaches the opposite wall slightly sooner. The difference over the length of an ordinary room is much too small for your ears to notice, but accurate instruments can measure it easily. Stretch the distance far enough and the change becomes more important. At around a comfortable indoor temperature, Sound in air moves at a little more than 340 meters each second. Cool the air substantially and the speed drops. Warm it and the speed rises. The change is gradual rather than sudden. There is no temperature at which sound suddenly decides to select a different gear. Each alteration in the microscopic state of the gas changes the rate at which pressure information moves through it. This is one reason that quoting the speed of sound as a single exact number can be misleading. The familiar value found in textbooks is usually based on particular atmospheric conditions. It is extremely useful, but it is not a universal speed attached permanently to sound. Ask for the speed of sound in air, and a physicist may quietly want to know the temperature before giving a very precise answer. Ask at a dinner party, and you may find that everyone suddenly becomes interested in the bread instead. The temperature effect is especially useful because it shows how sound speed can change without changing the substance itself. Earlier, moving from air to water or steel gave us very different speeds because the mechanical properties of the medium changed dramatically. Here, we keep ordinary air and simply alter its temperature. The composition remains broadly the same. It is still a gas, yet its microscopic state has changed enough to alter how efficiently a disturbance travels. One way to understand this is to return to pressure. Gas pressure comes from molecules moving and interacting. When the gas is compressed during a sound wave, its pressure rises. That compressed region pushes outward, which creates the restoring effect that allows the wave to continue. Warm gas has a different relationship between molecular motion, compression, and pressure from cold gas. A small disturbance can therefore produce a faster chain of responses. There is another interesting feature of sound waves that makes temperature especially relevant. The compression and expansion involved in ordinary sound happen quickly. A tiny region of air is compressed and then released before it has much opportunity to exchange heat with the surrounding environment. The gas briefly warms during compression and cools during expansion. Those thermal changes contribute to the pressure response that carries the wave. Sound propagation in a gas is therefore tied not only to mechanics, but also to thermodynamics, even though nothing about an everyday conversation feels particularly like a thermodynamics experiment. Every word you speak contains countless microscopic compressions and expansions in which pressure, temperature, and molecular motion are continually adjusting. Your ear receives the final pattern and interprets it effortlessly as language. The amount of physics required for someone to ask whether you remember to buy milk is frankly excessive, but nature has never shown much interest in simplifying itself for our convenience. The effect of temperature becomes even more interesting when the air is not all at the same temperature. Outdoors, uniform air is the exception rather than the rule. The ground absorbs sunlight. Buildings warm unevenly. Water surfaces heat and cool differently from land. Wind mixes layers of atmosphere. After sunset, the ground can cool rapidly, while air higher above remains warmer. These variations mean that sound may encounter different speeds along different parts of its path. When one part of a sound wave moves through slightly warmer air and another part moves through cooler air, the different portions do not advance at exactly the same rate. The wave can gradually change direction. This bending is known as refraction, and it can have surprisingly noticeable effects on what you hear over long distances. Consider a warm, sunny afternoon. The ground has absorbed energy from the sun and heated the air close to the surface. Air higher above may be cooler. Sound travelling near the ground therefore finds itself in a region where its speed can be greater below and lower above. Because different parts of the wavefront move at different speeds, the sound tends to bend in a particular direction. Under some conditions, that bending can carry sound upward and away from a listener on the ground. Now consider a calm night. The ground can lose heat quickly after sunset and become cooler than the air above it. The layer nearest the surface may then be colder while warmer air sits above. The pattern of sound speeds reverses. Sound that begins to spread upward can bend back toward the ground, allowing distant noises to reach listeners more effectively. This is one reason nights can sometimes seem acoustically different from days. A motorway that normally fades into the background may sound oddly present. A train can seem closer than it really is. Music from a distant outdoor event can arrive with surprising clarity. It is tempting to assume that nighttime simply makes everything easier to hear, because there are fewer competing noises, and that can certainly contribute. But atmospheric refraction can also play a role. The air has changed how it guides the sound. People noticed effects like these long before they understood the molecular explanation. Distant bells, cannon fire, voices and industrial noises could sometimes be heard from unexpected locations or fail to reach places where they seemed as though they should. The atmosphere was acting as a changing acoustic environment rather than a perfectly uniform container. Wind adds another layer of complexity. We often say that sound carries better downwind, which is broadly familiar from experience. But the interesting effect is not simply that the wind picks up the sound and blows it toward you like a leaf. Sound moves relative to the air, and the air itself moves relative to the ground. More importantly, wind speed often changes with height. Air higher above the ground may move faster than air close to the surface, because buildings, trees, and the ground create friction. If a sound travels with the wind, the upper parts of the wave can be carried differently from the lower parts. This variation can bend the sound toward the ground. Against the wind, the opposite bending can occur, sending more of the sound upward and creating a region near the ground where the source becomes harder to hear. Temperature gradients and wind gradients can operate at the same time, making real outdoor acoustics wonderfully complicated. This has practical consequences. Engineers predicting noise from airports, roads, wind turbines, factories, or construction sites cannot always assume that sound spreads through a uniform atmosphere. Weather conditions can influence where noise is heard and how strong it seems. A source that is acceptable under one set of atmospheric conditions may become more noticeable under another. The machinery has not necessarily changed. The path between the machinery and the listener has. Temperature also matters for measuring distance with sound. Suppose you send a sound pulse toward a surface and measure how long the echo takes to return. To convert that travel time into an accurate distance, you need an appropriate sound speed. If you assume a value suited to warm air while the actual environment is cold, your result will be slightly wrong. For short casual measurements, this may not matter, but precision instruments cannot ignore it. Ultrasonic distance sensors face this problem directly. These devices send pulses too high in frequency for human hearing and listen for the returning echo. They are used in equipment ranging from industrial systems to some parking sensors. The basic method relies on travel time. Since the speed of sound changes with temperature, a well-designed system may need temperature information if accurate distances are required over changing conditions. Musicians also encounter temperature through the behavior of air inside instruments. A flute, clarinet, trumpet, organ pipe, or other wind instrument depends on resonances in a column of gas. The instrument favors particular patterns of vibration based partly on its dimensions and partly on the speed of sound inside it. If sound speed changes, those resonant frequencies change as well. This is why wind instruments can shift slightly in pitch as they warm during playing. At the beginning of a rehearsal, the instrument may be cooler. As warm breath passes through it and the instrument itself warms, the air inside reaches a different temperature. Sound travels faster through that warmer air, changing the resonances. Musicians compensate through tuning and technique, often without spending the rehearsal discussing molecular kinetics, which is probably for the best. Pipe organs face a related challenge on a much larger scale. Their pipes depend on resonating air columns, and the temperature inside a large building can change. Organ builders and musicians have long had to deal with the fact that acoustics does not live separately from the weather and heating system. A grand instrument may have thousands of pipes, but every one of them is still using ordinary air as part of its physics. The human voice contains resonating air spaces too. Your vocal cords produce a basic vibration, but your throat and mouth shape the resulting sound by emphasizing certain frequencies. Temperature changes under ordinary circumstances are not dramatic enough to turn a winter conversation into something unrecognizable, yet the principle remains the same. The gas through which the sound moves helps determine the acoustic behavior of the space. Humidity also has an effect, although temperature is usually the more important everyday influence. Moist air contains a greater proportion of water vapor and a slightly different mixture of molecular masses than dry air. Because sound speed depends on the molecular properties of the gas, changing the composition can change the speed slightly. This sometimes surprises people because humid air feels heavier, yet at the molecular level water vapor is lighter than the nitrogen and oxygen molecules it replaces in the mixture. The effect of humidity is relatively modest for most daily situations, but acoustics often consists of many modest effects accumulating over distance. Temperature, humidity, pressure conditions, wind, ground surfaces, vegetation, buildings, and terrain can all influence what eventually reaches the listener. Pressure itself leads to an interesting point. We might expect sound to move much faster on a high-pressure day because the air is being squeezed more strongly. For an ideal gas at the same temperature, however, increasing the pressure also increases the density in a way that largely balances the change in restoring behavior. The speed of sound therefore depends much more directly on temperature and gas composition than on ordinary changes in atmospheric pressure. This is another example of why sound speed cannot be understood by looking at density alone. Increase the density of a gas by increasing its pressure while keeping its temperature fixed, and you have also changed how strongly the gas responds to compression. The two changes work together. Nature continues to insist that stiffness and inertia be considered as a pair. Altitude brings several of these effects together. As you climb through the atmosphere, pressure and density decrease, but temperature also changes. The local speed of sound follows the temperature particularly closely. This matters to aviation because aircraft performance is often described relative to the local speed of sound. An aircraft travelling at a certain speed over the ground may be comfortably below the speed of sound in one atmospheric condition and closer to it in another. Pilots and engineers therefore do not treat the speed of sound as one permanent number painted across the sky. They compare the aircraft with the sound speed in the air through which it is actually moving. This becomes increasingly important at high speeds because airflow around an aircraft depends strongly on whether pressure disturbances can move ahead of it. At ordinary speeds, the air in front of the aircraft receives pressure information in advance. The disturbance spreads outward faster than the aircraft approaches. Air has time to begin adjusting before the aircraft arrives. As the aircraft moves closer to the local speed of sound, that warning system becomes less effective. The aircraft begins catching up with its own pressure disturbances. Regions of compressed air can crowd together. The flow begins behaving in ways that cannot be understood by treating air as though changes are communicated instantly. Temperature therefore influences more than how long thunder takes to reach you. It helps set the pace at which the atmosphere can communicate mechanical information. That pace matters to musical instruments, echoes, outdoor noise, sonar-style measurements in air, and the aerodynamics of very fast vehicles. Thunder provides a particularly large natural example. Lightning suddenly heats a narrow channel of air to an extraordinary temperature. The air expands violently, producing a strong pressure disturbance that spreads outward as thunder. Near the lightning channel, the disturbance can be intense enough to behave as a shock wave. Farther away, it weakens into ordinary sound. The atmosphere between the lightning and the listener is rarely uniform. Temperature changes with height, winds move different layers, and the path can pass through kilometers of changing conditions. This contributes to the rolling, extended character of distant thunder. Different parts of the sound can follow different paths and arrive at different times, while the lightning channel itself may extend over a considerable distance and produce sound along its length. A nearby strike often produces a sharp crack because the travel paths are relatively short and the sound remains intense. A distant storm produces the long rumble we associate with thunder because the geometry and atmosphere spread the arrivals out. What begins as a sudden event becomes stretched in time by its journey through the air. Temperature gradients can even create regions where sound is surprisingly weak. If a wave bends upward away from the ground, a listener farther away may fall into an acoustic shadow where the direct sound is reduced. Move farther still, and changes in the atmosphere may bend some sound back down again. The result can be the odd experience of hearing a distant source clearly in one location, losing it somewhere else, and perhaps detecting it again beyond that. Historical observations of large explosions and volcanic eruptions have sometimes shown patterns like this, with sound heard at great distances while nearer regions reported less. The atmosphere can guide and refract powerful low-frequency waves across enormous scales. What appears to be empty air is actually a layered moving medium with changing acoustic properties. The same principle helps scientists study the atmosphere itself. Very low-frequency sound, often below the range of human hearing, can travel long distances and can be produced by events such as volcanic eruptions, large explosions, meteors, and severe weather. Monitoring these signals provides information not only about the source, but also about the atmosphere through which they travelled. Because temperature and wind influence their paths, acoustic observations can reveal something about conditions high above the ground. It is an elegant reversal of the ordinary problem. Usually we want to know the atmosphere so that we can predict what sound will do. In atmospheric acoustics, we can sometimes study what the sound did in order to learn about the atmosphere. Even indoors, temperature differences exist, although they are usually too small over short distances to produce dramatic sound bending. Warm air from a radiator rises. Cooler air can collect near windows or floors. A ceiling may be several degrees warmer than the lower part of a tall room. Sound crossing these layers experiences slightly different speeds, but reflections from walls and the short distances involved generally dominate what we notice. Outdoors, where distances become hundreds or thousands of meters, small differences accumulate. A tiny change in speed across a wavefront can gradually alter its direction. This is a recurring theme in wave physics. Small local changes can produce large effects if the wave has enough distance over which to respond. Temperature also reminds us that the molecules carrying sound are not arranged like a stationary mechanical machine. They are part of a thermal environment. Every compression caused by a sound is superimposed on molecular motion produced by heat. The ordered motion associated with the acoustic wave may be tiny compared with the random microscopic motion already present. Yet because the ordered changes are coordinated across large numbers of molecules, they can travel and carry recognizable information. Your voice can therefore survive a room full of chaotic molecular movement. A speaker creates incredibly small pressure variations. Those variations propagate through air whose molecules are racing randomly in every direction, and another person's ear extracts the organized pattern from that restless background. The air does not become orderly for the sound to pass. The sound is an organized disturbance riding through disorder. Cooling the air changes the background motion and therefore changes the wave speed, but it does not usually change the basic information encoded in the sound. A spoken word remains the same word. The frequencies produced by the source remain tied to the source. What changes is how far the wave travels during each cycle, because its propagation speed has changed. If the source keeps producing the same number of vibrations each second while the wave moves faster, the repeating pressure pattern becomes more spread out through space. In colder air, where the wave moves more slowly, the repeating pattern is slightly more compressed spatially. This happens automatically. The source does not need to know what temperature the air is. It simply vibrates, and the medium determines how the resulting wave is arranged. That distinction becomes useful whenever sound moves from one temperature region to another. The rhythm of the wave cannot suddenly change simply because the air ahead is warmer. Each cycle follows the one before it at the rate established by the source. Instead, the spacing between corresponding parts of the wave adjusts as the propagation speed changes. Because one side of an angled wavefront may enter the new region before the other side, the change in speed can rotate the direction of travel, producing the refraction we discussed earlier. What seems like a weather detail is therefore connected directly to the geometry of waves. Warm air makes sound faster. Uneven warming makes different parts of a sound wave faster by different amounts. Different speeds across the wave change its direction. That altered direction determines which listener hears the source and how strongly. It is worth noticing how far we have moved from the original picture of a sound simply flying through the atmosphere. The air is not a passive emptiness. Its molecules supply the pressure response that allows sound to exist. Their masses provide the inertia. Their thermal motion changes the rate of propagation. Their large-scale temperature distribution bends the path. Wind carries and reshapes that path further. Humidity changes the composition slightly. Every sound outdoors is negotiating a medium that has structure, motion, and weather. A warm summer evening and a freezing winter morning therefore do not provide precisely the same acoustic world. The difference may be subtle to human hearing at short range, but physically the atmosphere is offering a different speed limit to pressure disturbances. Thunder crosses the distance at a different rate. An echo returns at a slightly different time. A wind instrument settles into slightly different resonances. A fast aircraft encounters a different local sound speed, and there is a useful clue hidden in the phrase local sound speed. Sound speed belongs to the conditions where the wave is at that moment. If a wave climbs from one atmospheric layer into another, the relevant speed changes with it. There is no distant headquarters assigning one speed to the entire atmosphere. The wave responds continuously to the gas around it. That local dependence prepares us for an even stranger limit. Temperature can make sound faster or slower. Different gases can change its speed far more dramatically. Water and steel can carry it faster still. But all of these examples have something essential in common. There is always matter available to respond. There are molecules, atoms, or some other physical material that can be disturbed and can pass that disturbance onward. Remove the air from a room, and cooling is no longer the most important question. Remove enough matter, and there is no slower speed waiting underneath, no final crawl of sound through extreme emptiness. The relay itself begins to disappear because there is nobody left to make the handoff, which is why the next place to look is not another material at all, but the absence of one. Once the medium disappears, sound faces a problem that no amount of extra volume can solve. A louder speaker can create a stronger pressure disturbance in air. A larger explosion can push more violently on the surrounding atmosphere. A heavy hammer can send powerful vibrations through steel, but all of these examples still depend on something being there to move. Sound is not a substance that carries itself. It is a pattern of mechanical disturbance passed from one piece of matter to another, and if there is no matter available for the next handoff, the journey stops. This is why a vacuum is not simply a place where sound becomes very faint or extremely slow. In an ideal vacuum, ordinary sound does not travel at all. That can feel slightly strange because our everyday experience gives us almost no opportunity to encounter true emptiness. Even a room that looks empty is filled with air. Open a cupboard, and there is air inside. Look into an empty glass and the glass is full of gas. The spaces between buildings, inside caves, above oceans, and high in the atmosphere all contain particles. We are so thoroughly surrounded by matter that silence usually means there is no strong source of organized vibration nearby, not that the medium itself has disappeared. To understand what a vacuum does to sound, we have to imagine removing something that is normally present everywhere around us. Suppose an electric alarm is ringing inside a sealed transparent container. At first, the container is filled with ordinary air. You can see the alarm moving and hear the sound it produces. The vibrating parts push on nearby gas molecules. Those molecules create pressure changes that spread through the air, reach the wall of the container, make the wall vibrate slightly, and eventually create sound in the air outside. Nothing about this is unusual. The alarm is simply using several connected materials to send its mechanical disturbance toward you. Now imagine a pump gradually removing the air from inside the container. The alarm continues working. Its mechanism still moves. If it has a small bell or vibrating surface, that surface continues shaking just as before. But there are now fewer gas molecules around it. The moving surface has fewer particles to push against, and the pressure disturbance becomes harder to establish. As more air is removed, the sound transmitted through the remaining gas becomes weaker. Continue removing gas and the alarm can eventually become extremely difficult to hear, even though you can still see that it is operating. The source has not lost its ability to vibrate. What has been removed is the connection between the vibrating source and the surrounding wall. The alarm is trying to start a relay race, in which most of the runners have gone home. This kind of demonstration is one of the clearest ways to show that sound requires a medium. It also corrects a common misunderstanding. A vacuum does not somehow absorb sound after the wave has started. There is simply no continuous material available to support the ordinary pressure wave in the first place. A speaker cannot compress empty space in the same way that it compresses air. Move the speaker cone forward into a vacuum, and there is no cloud of gas molecules ahead of it becoming crowded. Move it backward, and there is no gas being left slightly more spread out. The mechanical process that creates airborne sound has lost the material it needs. The word vacuum can make this seem more absolute than real laboratory conditions usually are. Creating a perfect vacuum, meaning a region containing no particles at all, is extraordinarily difficult. Real vacuum chambers contain some residual gas. Interplanetary and interstellar space also contain particles, although often very few compared with the atmosphere near Earth. The important point is that as the amount of matter decreases, ordinary acoustic transmission becomes less effective. In the ideal limit of complete emptiness, there is no conventional sound wave because there is no material to compress, stretch, or otherwise disturb. This immediately explains why outer space is not filled with the sounds that films often give it. A spacecraft explodes in a movie and the audience hears a magnificent boom. Two ships fly past one another and engines roar. Weapons fire with satisfying blasts. These choices make perfect sense for entertainment, because a completely silent battle would feel oddly detached from what we are seeing. Real physics, however, does not provide an atmosphere just because the scene would benefit from one. Imagine two astronauts floating some distance apart in a vacuum. One of them strikes a metal tool against another object. The tool and the object vibrate. If the astronaut is touching them, those vibrations can travel through the suit and perhaps be detected through contact. But the sound cannot simply leap across the empty gap to the second astronaut as an ordinary pressure wave. There is no air between them to carry it. If the two astronauts were connected by a solid metal rod, the situation would change. Strike the rod at one end and mechanical vibrations could travel through the solid to the other astronaut. The surrounding space might still be nearly empty, but the rod provides a medium. The sound has found a physical route. This distinction is important because saying that there is no sound in space can be misunderstood to mean that nothing in space can vibrate. Objects in space can vibrate perfectly well. Spacecraft structures can shake. Planetary surfaces can carry seismic waves. Gas clouds can support pressure disturbances. Stars can oscillate. The claim is much more specific. Ordinary sound cannot cross a region of vacuum because a mechanical wave requires matter through which to propagate. Inside a spacecraft, of course, sound behaves normally because the cabin contains air. An astronaut can hear another crew member speak, hear fans, equipment, alarms, and all the tiny noises produced by machinery. Vibrations can also travel through the metal structure of the vehicle. In fact, spacecraft can be surprisingly noisy inside. The silence belongs to the vacuum outside, not automatically to everything associated with space. The same distinction applies to a spacesuit. An astronaut inside a pressurized suit is surrounded by gas. Their voice creates sound inside the helmet. A microphone converts that sound into an electrical signal. Radio waves then carry the information across the vacuum to another astronaut or to a spacecraft. At the receiving end, a speaker converts the electrical signal back into sound inside another pressurized environment. This is why astronauts can communicate even though sound itself cannot cross the space between them. The information changes carriers. It begins as mechanical vibration in one person's vocal system. It becomes sound in air. A microphone converts it into an electrical signal. Radio technology sends electromagnetic waves through space. a receiver converts the signal back into electrical activity, and a speaker recreates a pressure wave in air near the listener. The message crosses the vacuum, but the sound wave does not. That difference is easy to miss because we experience the whole process as conversation. One astronaut speaks and another hears the words moments later. From a human point of view, it feels as though the voice travelled across space. Physically, several different forms of energy and information were involved. Light has no problem with the vacuum because light is not a mechanical wave in matter. It is electromagnetic radiation. It does not require air molecules, water molecules, or a solid structure to pass its disturbance onward. That is why sunlight can cross the enormous distance between the Sun and Earth through regions containing very little matter. It is also why you can see an explosion in space without hearing it directly. This contrast between light and sound is visible during every thunderstorm. Light from a lightning flash travels through the atmosphere toward you at an extraordinary speed, while the sound wave depends on the mechanical response of the air and arrives much later. If the entire atmosphere between you and the lightning somehow vanished instantly, you could still see the flash. The thunder would have no ordinary acoustic route to your ears. There is a useful philosophical trap hidden here. People sometimes ask whether an explosion in space makes a sound if nobody's there to hear it. In physics, we can avoid the philosophical argument by being precise about what we mean by sound. If we mean a mechanical pressure wave travelling through a medium, then an explosion in a true vacuum cannot produce an airborne sound wave because there is no air. The exploding material itself may vibrate, fragments may collide, and gas released by the event may temporarily provide its own local medium, but there is no continuous atmosphere carrying a boom across empty space. Gas released during an explosion gives us an interesting borderline case. Suppose a violent event ejects a cloud of hot gas into a vacuum. Inside that expanding cloud, particles are present, so pressure disturbances can exist locally. Sound could travel through sufficiently dense portions of the gas. As the cloud expands, however, the particles become more widely separated, and the conditions for ordinary sound propagation change. There is no contradiction. Sound exists wherever matter provides the necessary mechanical connections. Space itself is not perfectly empty on most scales. Between planets there is thin gas, charged particles from the solar wind, dust and plasma. Between stars there is even more tenuous material. Scientists sometimes describe waves moving through these environments using language that sounds similar to acoustics. Plasmas can support different types of waves, some of which behave in ways related to pressure waves. But these are not the same as a person speaking through ordinary air, and the extreme thinness of much of space means that imagining it as a faint atmosphere is misleading. Our ears would be useless for directly listening across most of those environments. Human hearing evolved for the dense atmosphere near Earth's surface, where molecules collide frequently enough for ordinary sound waves to behave as we expect. Space operates under very different conditions. That helps explain why reducing pressure in a gas can eventually change the usefulness of our ordinary sound description. At normal atmospheric pressure, molecules collide frequently, and a smooth pressure wave is an excellent way to describe what happens. Remove more and more gas, and the average distance a molecule travels between collisions increases. Eventually the particles can become so sparse that the neat idea of a continuous fluid carrying sound begins to break down. A pressure wave relies on local regions of the gas behaving collectively. A region becomes compressed, pressure rises, and neighbouring regions respond. But if particles are separated by distances large compared with the scale of the disturbance, there may no longer be enough collisions for the material to act like the familiar continuous medium. The relay is no longer merely slow. The idea of a well-organised relay itself becomes less appropriate. This connects the everyday physics of sound with the microscopic nature of matter. Air seems continuous when we breathe it, or wave a hand through it, but it is made from separate molecules. At ordinary densities there are so many of them, and their collisions are so frequent that treating the gas as a smooth medium works beautifully. A vacuum reveals the limits of that approximation. Remove enough particles and the hidden graininess of matter becomes impossible to ignore. Vacuum technology therefore provides a useful way to study both sound and gases. Engineers create low-pressure environments for many reasons, including manufacturing, scientific experiments, electronics, and space simulation. Controlling vibrations in these systems can become a complicated problem because removing air only eliminates one transmission route. Mechanical vibration can still travel through the solid structure of the equipment. Imagine a vacuum pump connected to a chamber. The chamber may contain very little gas, yet vibrations from the pump can travel through metal pipes, supports, tables, and walls. An instrument inside could therefore experience mechanical noise, even though airborne sound transmission has been greatly reduced. The vacuum has silenced the gas, but the solids are still perfectly capable of carrying disturbances. This is why a quiet scientific instrument may need to be mechanically isolated as well as placed in a vacuum. Rubber mounts, carefully designed supports, suspended platforms, and other techniques can reduce vibrations passing through the structure. Anyone who has heard a washing machine vibrating through a floor already understands the basic problem. Matter is very good at finding alternate routes. The same issue appears in buildings. You can improve acoustic isolation between rooms by sealing air gaps, but footsteps may still travel through the floor. A vibrating machine may send energy through a wall. Low-frequency noise from a lift motor or ventilation system may travel through structural beams. Removing one path does not automatically remove them all. A vacuum chamber simply gives us an especially clear separation. Take away the gas and airborne sound becomes weaker, but solid-borne vibration remains. If you could suspend a ringing object inside a nearly perfect vacuum without any physical contact with the chamber, you would remove both the ordinary air route and much of the structural route. You might see the object vibrating while hearing almost nothing from it. There is something slightly unsettling about watching an obvious vibration without hearing the expected result. Our brains strongly associate visible impacts and movement with sound. Drop a glass and you expect a crash. Strike a bell and you expect a ring. A silent version feels wrong because nearly every such event in ordinary life occurs inside an atmosphere. The vacuum exposes just how much our intuition depends on air being present without our noticing it. The famous image of a bell in a vacuum works so well for exactly this reason. A bell does not contain sound as though sound were stored inside the metal and released when struck. The bell vibrates. Those vibrations need to disturb surrounding matter before an airborne sound wave exists. Put the same vibrating bell in air and you hear it. Put it in water and you can transmit the vibration differently. Attach it to a solid and the vibration can enter that material. Isolate it in an ideal vacuum and there is nothing nearby to carry the pressure disturbance. This gives us a useful way to separate source from sound. The source is the vibrating object. Sound is the mechanical wave created when that vibration enters a medium. They are related, but they are not the same thing. A guitar string can vibrate in a vacuum. A tuning fork can vibrate in a vacuum. A drum skin can move in a vacuum. Without surrounding matter, however, none of them can create the familiar airborne sound that would reach a distant ear. Even on Earth, this distinction matters for how loud different objects seem. A tuning fork held in the air may sound relatively quiet because its narrow arms do not move a large amount of air efficiently. Touch its base to a table and the table begins vibrating as a much larger surface. The sound becomes louder because the vibration is now better coupled to the air. The source was already moving, but the connection to the medium changed. Musical instruments are full of clever solutions to this problem. A guitar body, violin body, piano soundboard, drum shell, and many other structures help vibrations interact with the surrounding air. Without those structures, the original vibrating strings or components might produce much less audible sound. Instrument design is partly the art of persuading mechanical vibration to enter the atmosphere effectively. The vacuum does the opposite. It makes that transfer difficult by removing the atmosphere entirely. There is an interesting biological consequence as well. Human ears are pressure detectors designed to respond to a medium. The eardrum moves when changing air pressure reaches it. In a vacuum, Not only would there be no ordinary sound transmission, but exposing a person directly to vacuum would be extremely dangerous for reasons that go far beyond hearing. We do not need to imagine placing an unprotected ear in empty space to test the principle. Vacuum chambers and physical measurements can demonstrate it safely. Inside a sealed helmet, though, the ear works normally because the helmet maintains an atmosphere. If something taps the outside of the helmet, vibration may travel through the solid shell and then create sound in the air inside. This means an astronaut could potentially hear certain mechanical events connected directly to the suit, even though no airborne sound crossed the surrounding vacuum. The route matters more than the location. A person can be in space and still hear sound if matter connects the source to the ear. Remove that connection and the sound disappears. This becomes even clearer if we imagine a long spacecraft with two people in different compartments. If the compartments contain air, they can hear sounds transmitted through that air and through the structure. If a section between them is evacuated but the metal walls remain connected, some vibrations may still travel through the spacecraft itself. A vacuum only blocks the route that depended on the missing gas. It does not have a magical ability to erase vibrations from matter that still exists. The idea also helps explain why saying sound cannot travel in space is useful but slightly simplified. A better statement is that sound requires a medium and cannot travel through a perfect vacuum. Space contains many regions where matter exists, and mechanical waves can occur within that matter. On the surface of Mars, for example, there is an atmosphere, though much thinner and compositionally different from Earth's. Sound can travel there, but it behaves differently because the medium is different. On a planet or moon with no substantial atmosphere, airborne sound would be absent, though vibrations could still pass through the ground. If an astronaut stood on the surface of an airless moon and struck the ground with a tool, another astronaut standing nearby would not hear the impact through the non-existent atmosphere. But if both astronauts were in physical contact with the ground and had instruments capable of detecting the vibration, mechanical waves could travel through the solid surface. The world would be acoustically strange rather than completely free of vibration. Scientists already make use of this distinction with seismic instruments. A seismometer does not need air to hear in the everyday sense. It measures motion of the ground. On another world, impacts, internal geological activity or machinery could produce vibrations that travel through rock even where the surface above is essentially silent. The most useful lesson from the vacuum is therefore not merely that space is quiet, it is that sound belongs to matter. Remove matter and the mechanism disappears. Add matter back and sound becomes possible again. The type of matter determines what kind of disturbance can travel and how quickly. Air, water, steel, rock, and biological tissue each provide different versions of the same basic service. They supply neighbouring pieces capable of pushing, pulling, compressing, stretching, and responding. A vacuum supplies none of those things. That also gives us a clean answer to an old question about whether sound itself has a universal speed limit. It does not. Different media permit different sound speeds because their mechanical properties differ. In a vacuum, there is not an infinitely large sound speed or an extremely small one. There is no ordinary sound speed to assign because the wave cannot exist there in the usual sense. The absence of sound in a vacuum makes the behaviour of fast objects in air more interesting rather than less. As long as an aircraft is inside the atmosphere, every part of its motion pushes on a medium that can carry pressure information. The air ahead of the aircraft can be warned by those disturbances that something is approaching. At low speed, those pressure changes spread comfortably ahead of the vehicle. The air begins adjusting before the aircraft reaches it, but an aircraft can keep accelerating. Eventually it can move almost as quickly as the pressure disturbances themselves. The air can no longer send information far ahead in the same comfortable way. Waves begin to crowd together. Pressure changes become much stronger and more abrupt. Go faster still, and the aircraft moves ahead of some of the disturbances it creates, leaving a structured region of compressed air behind it. Nothing about this requires an invisible wall in the sky. The dramatic effects appear because sound has a finite speed in the medium and an object is approaching or exceeding that speed. The very property that vanished in the vacuum becomes crucial again the moment matter returns, because once air is present, there is a definite pace at which one region can tell the next that something is coming. Once air is present again, sound has a speed, and that speed creates a very interesting possibility. An object moving through the atmosphere can eventually move as fast as the pressure disturbances it creates. Push the object a little faster, and it begins to outrun them. This is where ordinary sound turns into something much more dramatic. Shock waves appear. Pressure changes pile together. Sonic booms reach the ground. The phrase sound barrier starts showing up, usually accompanied by photographs of fast aircraft surrounded by clouds and headlines suggesting that something has punched through an invisible wall. There is no wall, of course. The atmosphere has not constructed a secret barrier and placed it in front of the aircraft. What exists is a limit on how quickly the surrounding air can communicate a disturbance, and once an object competes with that speed, the behaviour of the air changes in ways that are impossible to ignore. To see why, imagine an aircraft moving quite slowly through the atmosphere. Long before the nose of the aircraft reaches a particular region of air, pressure disturbances created by the approaching vehicle can travel outward ahead of it. The molecules farther forward begin responding before the aircraft physically arrives. They are pushed slightly, pressure changes spread, and the airflow gradually adjusts around the approaching object. The aircraft is moving, but the information about its motion is moving faster. In a sense, the air has advance warning. This happens with any object moving more slowly than sound. A car on a motorway creates pressure changes. A bird moving through the air creates them. Wave your hand and you disturb the atmosphere around it. In each case, sound speed is much greater than the speed of the object, so those disturbances can spread away in every direction and comfortably outrun the source. The surrounding air has time to react. Now imagine increasing the aircraft speed. The pressure disturbances still move through the air at the local speed of sound, but the aircraft begins following them more closely. Each new disturbance starts from a position farther along the flight path, because the aircraft has moved before producing it. The pressure waves in front of the aircraft therefore become more crowded. At first, this compression is modest. The aircraft is still slower than sound, so information can continue moving ahead. But as the aircraft approaches the sound speed, the difference between the speed of the aircraft and the speed of its pressure, disturbances become smaller. The waves have less opportunity to escape from one another. Pressure changes begin accumulating in the same region. This is why the speed of sound matters so deeply to aerodynamics. It is not simply another speed to compare with the aircraft's speed. It is the rate at which the air can communicate changes in pressure. When the aircraft moves much more slowly than that communication speed, the airflow can adjust smoothly. When the aircraft moves close to that speed, parts of the flow begin receiving information too late to respond gently. Engineers describe an aircraft speed relative to the local speed of sound using what is called a Mach number. The name comes from the physicist Ernst Mach, whose work helped clarify the behaviour of fast-moving objects and shock waves. A Mach number below 1 means the object is moving more slowly than the local sound speed. Mach 1 means it is moving at the local speed of sound. A value above 1 means it is moving faster. The word local is important. Mach 1 is not one permanent speed everywhere on Earth. The speed of sound changes with atmospheric temperature, so the actual speed corresponding to Mach 1 changes with altitude and weather conditions. An aircraft high in cold air encounters a different sound speed from an aircraft moving through warmer air closer to the surface. Saying that an aircraft is travelling at Mach 1 therefore tells us how it compares with the air around it, not one universal ground speed. As an aircraft approaches this region, another complication appears. Air does not move around every part of the aircraft at the same speed. Even if the aircraft itself is still moving below the sound speed, airflow over parts of a wing can accelerate enough to become locally supersonic. Some regions may have air moving below the sound speed, while nearby regions reach it or exceed it. This mixed condition is known as transonic flight, and it can produce complicated pressure changes and shock waves before the aircraft as a whole is comfortably supersonic. This caused serious difficulties for early high-speed aircraft. Pilots approaching the sound speed encountered rapidly changing aerodynamic forces, increased drag, vibration, and control problems. The phrase sound barrier grew partly from these experiences. It seemed as though aircraft had reached a physical threshold that resisted further acceleration. Some people even wondered whether controlled flight beyond the sound speed might be impossible. The problem was not an invisible barrier. It was that aircraft designed for slower flight were entering a regime where compressibility could no longer be treated as a minor detail. At lower speeds, engineers can often approximate air as though its density does not change very much while flowing around an aircraft. Near the speed of sound, that becomes a poor assumption. Pressure disturbances compress the air significantly. Shock waves form. Forces on the wings and control surfaces change. Aircraft had to be designed for this new behaviour. Wings became thinner. Shapes were adjusted to control airflow. Control surfaces and structural designs improved. Engines became more powerful. The problem was not persuading nature to remove a wall. It was learning how to fly through air that behaves differently when pressure information can no longer remain comfortably ahead of the vehicle. When an aircraft finally moves faster than sound, the geometry of its disturbances changes completely. Imagine the aircraft creating a pressure pulse at one moment. That pulse spreads outward through the air. A short time later, the aircraft has moved forward and creates another pulse. Because the aircraft itself is moving faster than those pulses can travel through the medium, it gets ahead of them. The expanding disturbances are left behind in a pattern that overlaps along a surface, extending outward from the flight path. Instead of pressure information spreading ahead of the aircraft, the disturbances accumulate into a sharp boundary. This boundary is a shock wave. A shock wave is not simply a very loud, ordinary sound wave. Across a shock, properties such as pressure, density, and temperature change over a very short distance. The air on one side is in a noticeably different condition from the air on the other. The transition is abrupt because the disturbance has become compressed into a narrow region. The effect can be compared with the wake behind a boat, although the physics is not identical. A boat moving through water creates waves that spread outward. If the boat moves, the pattern of those waves forms a wake behind it. A supersonic aircraft produces a three-dimensional version involving pressure disturbances in the air. Instead of a flat V-shaped wake on water, the aircraft is associated with a cone-shaped pattern of shock waves extending behind it. This is where one of the most common misunderstandings about sonic booms appears. People often imagine that an aircraft produces one boom at the exact moment it breaks the sound barrier, rather like bursting through a sheet of glass. After that moment, they assume the aircraft continues silently while travelling faster than sound. That is not what happens. A supersonic aircraft continuously creates shock waves as long as it continues moving through the atmosphere faster than the local speed of sound. The shock pattern travels with the aircraft. When that pattern sweeps across an observer on the ground, the observer hears a sonic boom. Someone standing many kilometers away can therefore hear the boom long after the aircraft first accelerated through the sound speed. The aircraft may have been supersonic for quite some time. What matters is the moment when the shock wave reaches that particular listener. Imagine a fast aircraft travelling in a straight line over a large landscape. People along a broad path beneath and beside the route may hear the boom at different times. Each person hears it when the shock structure passes their location. The aircraft is effectively dragging its acoustic disturbance across the ground. This is also why sonic booms can be heard even when the aircraft itself seems far ahead. The sound is not coming straight backward from the current aircraft position in the way an ordinary engine noise might. The listener is encountering part of the shock cone produced along the flight path. A typical sonic boom may contain more than one strong pressure change because different parts of the aircraft create important disturbances. The nose produces one pattern. Wings, engine inlets, and other surfaces contribute additional pressure changes. The rear of the aircraft can produce another major transition. At the ground, these disturbances may combine into the familiar double boom, sometimes associated with supersonic aircraft. The exact sound depends on aircraft shape, size, altitude, speed, atmospheric conditions, and the position of the listener. A small, slender aircraft does not necessarily create the same pressure signature as a larger one. Engineers interested in quieter supersonic flight study how the vehicle shape controls the way shock waves form and combine. This has become important because sonic booms are not merely interesting noises. Strong pressure changes can disturb communities over wide areas. They can rattle windows, startle people and animals, and in sufficiently strong cases contribute to minor structural effects. These concerns have historically limited routine supersonic flight over populated regions. Designers have therefore explored ways to reduce the intensity of the boom. Instead of allowing several shock waves to combine into one or two strong pressure jumps, an aircraft can be shaped so that the pressure changes are distributed more gradually. The aim is not to eliminate the basic physics of supersonic motion, because an aircraft faster than sound must still disturb the surrounding air. The goal is to control how that disturbance reaches the ground. This brings us back to the aircraft's shape itself. At ordinary speeds, a rounded nose can guide air around an object without creating the same kind of strong shock structure. At supersonic speeds, shapes that appear sharp and slender often have advantages because they can manage compression more gradually. The precise design is complicated, but the basic reason is familiar now. The air cannot receive pressure information far ahead of the approaching vehicle, so the geometry of how the vehicle first pushes on the air becomes extremely important. Supersonic aircraft are not the only things that create shock waves. Bullets can travel faster than sound. The sharp crack associated with some high-speed projectiles can include a shock wave produced along the projectile path. Meteors entering the atmosphere at enormous speeds generate powerful shocks. Spacecraft returning through the atmosphere do the same. Explosions can create shock waves when pressure changes are sufficiently intense. Lightning can also produce shock behaviour. The electrical discharge heats a narrow channel of air extremely rapidly. The hot gas expands violently and generates a strong pressure disturbance. Close to the lightning channel, that disturbance behaves more like a shock wave. As it spreads outward and weakens, it gradually becomes the ordinary sound wave we hear as thunder. This shows that a shock wave does not always require a solid object moving through the air faster than sound. What matters is creating a disturbance so strong or so rapidly moving that the pressure change becomes concentrated into a sharp front. A powerful explosion can do this even though there is no aircraft involved. The concept of a sound speed is still central, because it tells us how rapidly small pressure disturbances normally propagate through the medium. A shock appears when the changes become too abrupt for the ordinary gentle wave picture to remain adequate. There is an interesting way to think about this in terms of communication. Imagine air as a crowd in which each person can warn nearby people that something is approaching. At low aircraft speed, the warning moves through the crowd faster than the aircraft, so people far ahead know about it before it arrives. Near the sound speed, the aircraft nearly catches the warning. The message and the object arrive almost together. Above the sound speed, the aircraft moves into regions that have received no pressure warning from the aircraft itself. The abrupt arrival produces a much stronger response. Again, real molecules are not standing in rows sending messages, but the comparison captures why the sound speed acts like a communication limit for pressure changes in the gas. The air cannot adjust smoothly to something if information about the disturbance cannot get there first. This same idea matters beyond aviation. In astrophysics, gases can move at speeds above or below their local sound speed. Flows around stars, supernova explosions, jets, and gas falling toward compact objects can all involve shock waves. The temperatures and compositions are radically different from the atmosphere near Earth, but the underlying question is recognizable. How fast is the material moving compared with the speed at which pressure disturbances can propagate through it? A flow moving more slowly than sound can communicate pressure changes upstream. A supersonic flow cannot easily send that information against the direction of motion. This difference changes the entire behavior of the system. Something similar occurs in rocket nozzles. Hot gas is accelerated to very high speeds as it expands. Engineers carefully shape the nozzle because the gas can pass through the sound speed and become supersonic. Pressure, density, temperature, and flow speed change together. Shock waves can appear if the exhaust conditions do not match the surrounding atmosphere properly. Those bright patterns, sometimes visible in powerful rocket or jet exhausts, are connected to pressure adjustments in supersonic flow. The exhaust can expand too much or too little, compared with the surrounding air, leading to a sequence of compression and expansion structures. What looks like a decorative pattern behind the engine is actually the gas repeatedly trying to adjust itself, while moving faster than its own pressure information can conveniently travel upstream. Even without aircraft or rockets, a simpler everyday analogy can be found in waves on water. Throw a small object into still water, and ripples spread outward. Move a disturbance slowly across the surface, and waves can travel ahead. Move fast enough relative to the relevant wave speed and a wake pattern forms. A fast boat produces the familiar angled wake trailing behind it. The mathematics and details of water surface waves differ from sound waves, but the visual comparison helps. A moving source leaves overlapping disturbances behind because it is competing with the speed at which waves propagate through the medium. This is why photographs of aircraft apparently surrounded by a circular cloud can sometimes be misunderstood. The cloud is often described as the aircraft breaking the sound barrier, as though we are seeing the sound barrier itself. In reality, visible condensation can appear when pressure changes around a fast aircraft cause the local air temperature to fall enough for water vapour to condense. Under suitable humidity conditions, a temporary cloud forms. Such a cloud may appear near transonic or supersonic conditions because strong pressure changes are present, but the cloud is not a visible shock wave and it is not a shattered sound barrier. It is condensed water revealing part of the pressure environment around the aircraft. The phenomenon depends strongly on humidity and atmospheric conditions, which is why aircraft can travel at similar speeds without always producing the same dramatic cloud. The sound barrier phrase survives because it is vivid, and it captures something historically real about the difficulty engineers once faced. But a better mental picture is not a wall. It is a traffic problem for pressure waves. At low speed, every disturbance has plenty of room to move ahead. Near the sound speed, the traffic becomes crowded. At and above it, the disturbances pile into shocks. This picture also clarifies why the sonic boom does not stay permanently attached to one exact speed. Once the aircraft is supersonic, the angle and structure of the shock pattern depend on how much faster than sound it is travelling. At speeds only a little above the sound speed, the shock cone spreads relatively broadly. At much greater supersonic speeds, the pattern becomes narrower behind the vehicle. An observer must lie in the path of that pattern to hear the strongest boom. The aircraft may be visible in one part of the sky, while the sound seems to arrive from another direction or at another time. Just as thunder arrives after lightning, finite sound speed separates what you see from what you hear. The difference is especially striking for very fast objects. A supersonic aircraft can pass overhead before its strongest acoustic signal reaches you. A high-speed projectile can produce a crack that seems disconnected from the source position. The visual event and acoustic event are telling you about different travel paths and different propagation speeds. Sound speed, therefore, gives the atmosphere a kind of internal timing system. Every mechanical disturbance must obey the rate at which pressure can spread through the gas. An object slower than that rate remains acoustically connected with the air ahead of it. An object faster than that rate leaves its disturbances behind in a compressed pattern. There is no rule saying objects are forbidden to exceed the speed of sound. Sound is not like light in relativity, where the speed of light in vacuum plays a fundamental role in the structure of space and time. The speed of sound is a property of a medium. An aircraft can exceed it because the aircraft is not required to move by passing its own motion from one air molecule to another in the way a sound wave does. This difference is important. If sound travelled at a universal fundamental speed that nothing could exceed, supersonic flight would be impossible. Instead, the sound speed is set by the stiffness and inertia of the local material. Build an engine powerful enough and an aircraft shaped appropriately, and it can move faster than the pressure waves in the surrounding gas. Change the gas and the comparison changes, change the temperature and it changes again. An object described as supersonic in one medium might be subsonic relative to another medium with a higher sound speed. The label belongs to the relationship between object and medium. This also means that there is no single ultimate speed of sound across nature. Sound through water has one characteristic range. Sound through steel can be much faster. Other solids can carry mechanical disturbances faster or slower, depending on their properties. In each case, an object would have to be compared with the wave speed of that particular material if we wanted to describe its motion as subsonic or supersonic relative to those disturbances. Inside stars and giant planets, the local sound speed can become vastly greater than it is in Earth's atmosphere, because the pressures, temperatures, densities, and states of matter are completely different. Scientists use sound speed as a way of understanding these environments. In the Sun, pressure waves can move through the hot plasma and create oscillations that can be studied from afar. By observing patterns on the solar surface, researchers can infer information about conditions inside the Sun, rather like using seismic waves to investigate Earth. Once again, sound and related pressure waves become tools for exploring matter we cannot directly reach. That brings us back to the question that started this entire journey. Where does sound get its speed from? The answer was never hidden in the sound source. A violin does not decide the speed of its note. A speaker does not choose how quickly its music crosses the room. Thunder does not receive a special travel speed from lightning. The medium sets the pace. In air, pressure and molecular inertia establish one speed. Warm the air and that speed changes. Replace air with water, and the much greater resistance to compression changes it again. Move into a stiff solid and mechanical disturbances can travel faster still. Remove matter entirely and ordinary sound loses the ability to travel at all. Then, once an object moves through that matter quickly enough, the same speed that once seemed like a simple textbook, fact becomes an important boundary in the behaviour of the flow. Pressure waves crowd together, shock fronts form, sonic booms spread outward. Air that easily carried a quiet conversation across a room becomes the same medium capable of producing some of the most powerful acoustic disturbances we can hear. The remarkable part is that the quietest whisper and the crack of a sonic boom are built from the same basic machinery. Matter is disturbed. Neighbouring matter responds. Pressure changes move onward. The difference is one of strength, geometry, and whether the source is moving slowly enough for those disturbances to escape ahead, or rapidly enough to catch them. So when a distant aircraft passes overhead and its sound arrives later, when thunder follows a flash, when a voice travels through a room, or when a tap moves through a metal pipe faster than it reaches you through the air, the same question is sitting underneath every example. How quickly can this material pass a disturbance from one place to the next? Once that is the question, the speed of sound stops looking like a number that nature simply happened to choose. It becomes a description of the medium itself, of how strongly matter pushes back when disturbed, and how quickly its mass can respond. And whenever something tries to move through that medium faster than the response can spread, the air has no way to quietly get out of the way in advance. The disturbances collect, the pressure rises sharply, and the ordinary relay of sound becomes a shock.